September 11th, 2025. While NASA's Near-Earth Object Program tracked 34,157 asteroids, while ESA's SOHO spacecraft beamed down 847 gigabytes of solar observation data, while 7 automated sky surveys, equipped with tens of millions of dollars in technology, scanned the heavens for threats, for anomalies, for anything new. While all of that happened, a comet bright enough to see with a $20 pair of binoculars was hiding in plain sight. And it took one man, an amateur, in Ukraine, reviewing publicly available data on his laptop, to find it. His name is Vladimir Bezugliy. And on September 11th, 2025, at 0947 UTC, he submitted an observation report that would, within 17 hours, be confirmed by the Minor Planet Center and assigned the designation C2025 R2 SWAN, a comet, already magnitude 6 to 7, already developing a tail, already active, already visible to anyone with binoculars who knew where to look, but nobody was looking. Nobody except Vladimir Bezugliy. Now, before we go any further, before I walk you through what happened over the next 28 days and what's going to happen in 11 more, I need you to do something. Hit that like button, subscribe to this channel, and tell me in the comments where you're listening from right now, what time it is where you are, and whether you think NASA missed this comet or ignored it. Just drop a word or two, because what I'm about to show you raises a question that 28 days later, nobody at NASA, nobody at ESA, nobody at any of the institutions we fund to watch the sky has answered. How does a magnitude 6 comet, bright enough to see with binoculars, with a developing tail, on a trajectory that brings it within 40 million kilometers of Earth, go completely undetected until an amateur flags it? Let's start with what we know for certain. September 11th, 2025, 0947 UTC. Vladimir Bezugliy is reviewing images from SOHO, the Solar and Heliospheric Observatory, a joint NASA-ESA spacecraft that's been staring at the sun since 1995. SOHO has a coronagraph, an instrument that blocks out the sun's direct light so scientists can study the solar corona and the space immediately around the sun. And over the years, SOHO's coronagraph has discovered hundreds of comets, most of them sun grazers, small, faint objects that dive toward the sun and are vaporized in its heat. But this wasn't a sun grazer. Bezugliy saw something in the SOHO images that didn't fit the pattern. A bright, fuzzy object with a tail. A coma, the glowing cloud of gas and dust that forms around a comet's nucleus when it's heated by the sun. And it was moving, not toward the sun, away from it, on an orbit that would take it through the inner solar system and then back out into the darkness. He ran preliminary calculations. He checked the position against known comets, against asteroids, against everything cataloged. Nothing matched. This was new. He submitted his report. And here's where it gets interesting. Within 17 hours, the Minor Planet Center confirmed it. 17 hours. That's fast. Remarkably fast. The Minor Planet Center doesn't hand out comet designations lightly. They need multiple independent observations, position measurements from different observers, preferably in different locations. Enough data to confirm that what's being reported is real, not a processing error, not a misidentified known object, not a faint star or a cosmic ray hit on the detector. 17 hours means other observers jumped on this immediately. It means the object was bright, obvious, unmistakable once people knew to look for it. It means this wasn't some faint smudge that required professional telescopes and hours of exposure time to detect. This was magnitude 6, maybe magnitude 7 depending on who you ask and what equipment they were using. But either way, right on the threshold of naked eye visibility, under perfectly dark skies, far from any city, with no moon in the sky, and your eyes fully adapted to darkness, magnitude 6 objects are just barely visible as faint patches of light. With binoculars, easy, clear, unmistakable. So the question stands: if this comet was magnitude 6 or 7 when it was discovered, if it already had a developing tail visible in SOHO images, if it was bright enough that multiple independent observers confirmed it within hours once they knew where to look, why didn't NASA find it first? SOHO is a NASA ESA mission. NASA has scientists reviewing that data. ESA has scientists reviewing that data. The images are publicly available, yes, but they're also being analyzed by professionals whose literal job description is to identify objects near the sun, to track solar activity, to monitor space weather, and yes, to flag comets when they appear in the coronagraph field of view. And yet, an amateur found this first. Now here's what makes this even more confusing. NASA's Near-Earth Object Program, run out of the Jet Propulsion Laboratory, has a specific mandate: find, track, and characterize all near-Earth objects. Not just the ones that pose an impact threat, all of them. Asteroids, comets, anything that comes within 1.3 astronomical units of the sun. That's their job. That's what Congress funds them to do. That's what billions of dollars in automated sky surveys, telescopic arrays, and data processing pipelines are designed to accomplish. C-2025 R2 SWAN is a near-Earth object by that definition. It will pass within 0.267 astronomical units of Earth on October 20th. That's well within the monitoring zone. That's an object NASA should have flagged months ago, when it was still faint, still far out, still approaching. But they didn't. Or if they did, they didn't announce it. They didn't catalog it. They didn't add it to the public database of near-Earth objects. They didn't issue a press release. They didn't update their website. They didn't send out an alert to the amateur astronomy community saying, "Hey, there's a comet incoming. Here's its trajectory. Here's when it'll be brightest. Here's how to observe it." Nothing. Radio silence. And when Vladimir Bezugliy found it and submitted his report, when the Minor Planet Center confirmed it 17 hours later, when amateur astronomers around the world started pointing their telescopes at it and taking photographs and posting those photographs on Reddit and Twitter and astronomy forums, NASA still said nothing. No press release. No update on the Near-Earth Object Program website. No announcement from JPL or from NASA headquarters or from any of the scientists whose names are attached to SOHO publications. Silence. 28 days of silence. Now let's talk about what happened in those 28 days. Because while NASA stayed quiet, the comet didn't. By September 15th, just 4 days after discovery, amateur observers were reporting brightness estimates. Magnitude 7, maybe magnitude 6.5. Still faint, but brightening. The tail was visible in long exposure photographs, stretching maybe a degree or two across the sky. Not spectacular yet, but growing. By September 22nd, 11 days after discovery, something changed. Predictions for the comet's peak brightness, predictions that had initially suggested magnitude 5 or maybe magnitude 6 at best, were suddenly revised. Magnitude 4, some astronomers were saying. Maybe even magnitude 3.5, if the brightening trend continued. That's a full magnitude brighter than the initial estimates. In astronomical terms, each magnitude represents a factor of about 2.5 in brightness. So a shift from magnitude 5 to magnitude 4 means the comet is now expected to be 2.5 times brighter than originally thought. A shift to magnitude 3.5? Nearly 4 times brighter. Why the revision? What data came in between September 15th and September 22nd that caused such a dramatic change in predictions? I don't know. Because nobody published an explanation. No paper. No technical note. No forum post from a professional astronomer saying, here's what we observed. Here's why we revised the numbers. Just a quiet update to the prediction models and a few mentions in amateur astronomy circles that the comet might be brighter than expected. By October 3rd, less than a month after discovery, observers were reporting a tail length exceeding 5 degrees. 5 degrees. That's 10 times the width of the full moon. That's a tail stretching across a noticeable fraction of the sky, visible even in areas with moderate light pollution if you know where and when to look. And as of today, October 9th, 28 days after discovery, the tail may have grown to 6 degrees or more. The comet is currently estimated at magnitude 6, maybe magnitude 5.5, already visible in binoculars to anyone in the southern hemisphere or equatorial regions who gets up a few hours before dawn. And still, NASA has said nothing. No press release, no observation guide, no public outreach, nothing. But here's the thing, NASA didn't just stay silent about this comet. They stayed silent in a way that raises questions. Because when Comet C 2020 F3 Neowise was discovered in March 2020 and predicted to become bright by July, NASA put out press releases. They published observation guides. They posted images from spacecraft. They engaged the public. Neowise became one of the most photographed comets in history, visible even from cities, and NASA made sure people knew about it. When Comet C 2022 E3 ZTF was discovered in March 2022 and predicted to become visible to the naked eye in early 2023, NASA talked about it. Not as much as Neowise, but enough. Press releases, updates, a few articles on the NASA website, enough that people who follow space news knew it was coming. But SWAN, nothing. And it's not just NASA. ESA, the European Space Agency, whose spacecraft provided the data that led to this discovery, they've been just as quiet. A brief mention on the SOHO mission page, a couple of tweets from individual scientists, but no coordinated announcement, no press event, no European equivalent of a NASA press release. Why? Is it caution? Is it embarrassment? Is it because this comet slipped through the cracks of multiple detection systems and nobody wants to draw attention to that fact? Or is it something else? Now I want to be clear about something. I'm not suggesting there's a conspiracy here. I'm not claiming NASA or ESA is hiding some sinister truth about this comet. But I am asking a question, a simple question. Why has there been so little institutional response to a comet that's potentially the brightest in years? That was discovered less than 40 days before its closest approach to Earth. And that was found not by professionals, but by an amateur? Because here's what the silence creates. It creates a vacuum. And in that vacuum, people speculate. People ask questions. People wonder if there's more to the story than what's being said. Or, in this case, than what's not being said. And when you look at the numbers, when you really dig into the details of this discovery, the silence becomes even more conspicuous. SOHO's coronagraph has discovered over 4,000 comets since 1996. Most of them are faint sun grazers that were never going to be visible from Earth. But occasionally, SOHO spots a comet that's bright, that's on a trajectory, taking it through the inner solar system, that has the potential to become a naked eye object. How often does that happen? How often does SOHO's coronagraph catch a comet that's already magnitude 6 or 7, already developing a tail, already on its way to becoming one of the brightest comets in years. Not often. Maybe once every few years. Maybe less. And when it does happen, when SOHO captures images of a potentially spectacular comet, you'd expect that to be news. You'd expect NASA and ESA to be excited about it. You'd expect them to talk about it, to promote it, to engage the public with a rare opportunity to see something beautiful in the night sky. Instead, silence. Vladimir Bezugliy found this comet on September 11th. He submitted his report. It was confirmed within 17 hours. And in the 28 days since, the story has been told not by institutions, but by individuals. By amateur astronomers tracking the comet's brightness. By astrophotographers capturing its tail. By forum users calculating orbits and sharing predictions. By YouTubers like me trying to piece together what's happening and why nobody from NASA or ESA seems willing to talk about it. And here's the strangest part. This comet, C 2025 R2 SWAN, hasn't been in the inner solar system for approximately 1,400 years. Its orbital period is calculated at around 14 centuries. The last time it passed through, the last time it swung around the sun and became visible from Earth, was around the year 625 CE, the time of the Prophet Muhammad, the Tang dynasty in China, the Dark Ages in Europe, 1400 years. Think about that. 1400 years ago, there were no telescopes, no cameras, no way to study a comet in detail, just naked eye observations, recorded in fragmentary historical texts, many of which have been lost to time. And now it's back, for the first time in 14 centuries. And we have the technology to study it, to photograph it, to analyze its composition, to understand what it's made of and where it came from, to capture a moment in cosmic history that won't repeat for another 1,400 years. And NASA's response is silence. In 11 days, on October 20th, 2025, Comet SWAN will make its closest approach to Earth. It will be at its brightest. Its tail will be at maximum extension. And anyone with binoculars, anyone with a dark sky, anyone who takes the time to look up and find it, will be able to see something that hasn't been visible from Earth since the 7th century. And the institutions we fund to tell us about these things, they're not saying a word. So why am I telling you this? Why am I walking you through the timeline, the numbers, the silence? Because in 11 days, we're going to find out what this comet really is. We're going to see if it reaches magnitude 4, like the revised predictions suggest, or if it exceeds that, or if it surprises us in some other way, the way comets sometimes do. And whatever happens on October 20th, the data will be there. The observations will be made. The photographs will be taken by amateurs, by backyard astronomers, by people like you who decide to go outside and look, because that's how this story is being told. Not by NASA, not by ESA, but by individuals, by the global community of people who care about the sky, who track these events, who share what they see. Vladimir Bezugliy found a comet on September 11th. Magnitude 6, already bright, already active, already on its way to becoming one of the most significant cometary events in years. And NASA missed it, or didn't announce it, or chose not to talk about it. 28 days later, we still don't know which. But in 11 days, on October 20th, the comet won't care what NASA says or doesn't say. It will reach its closest approach. It will shine. Its tail will stretch across the sky, and we'll all be watching. The silence continues, but the comet is coming. September 11th, discovery. September 12th, Confirmation. 17 hours, and then silence. Not complete silence. Amateur astronomers were talking. Forum posts were appearing. Reddit threads were accumulating observations. But from the institutions, from NASA, from ESA, from the professional observatories with million-dollar budgets and teams of PhD scientists, there was nothing. No press release, no coordinated announcement, no technical briefing explaining what had just been found and what it meant. Just quiet. Now let's walk through the timeline. Because when you lay it out, day by day, hour by hour, something doesn't add up. There's a gap. A week where the comet changed, where predictions were revised, where something happened that nobody has publicly explained. September 11th, 2025, 0947 UTC. Vladimir Bezugliy submits his observation report. The comet is designated SWAN 25b temporarily, pending official confirmation. Initial estimates place it at magnitude 7 to 7.5. Faint, but detectable with binoculars. A tail is visible in the SOHO images, estimated at 2 degrees long. September 12th, 2025. The Minor Planet Center officially confirms the discovery and assigns the designation C2025 R2 SWAN. 17 hours from submission to confirmation. That's fast. Unusually fast. The Minor Planet Center typically takes days, sometimes weeks, to process new comet reports, especially when the object is faint or the observations are preliminary. But 17 hours? That means multiple independent observers jumped on this immediately. That means confirmation observations came in quickly, from different locations, with different equipment. That means this comet was obvious, unmistakable, bright enough that anyone who pointed a telescope at the right coordinates could see it. So why didn't professional observers find it first? September 12th is also the date of perihelion, the comet's closest approach to the Sun. Distance, 0.5 astronomical units. That's about 75 million kilometers. For reference, Mercury's average distance from the Sun is 0.39 AU. So SWAN passed the Sun at a distance greater than Mercury's orbit, but not by much. Close enough for intense solar heating. Close enough to drive rapid outgassing from the nucleus. Close enough to make the comet active, bright, developing. And here's something interesting. Perihelion happened one day after discovery, which means Vladimir Bezugliy found this comet at almost the exact moment it was reaching its closest point to the Sun. That's lucky, or suspicious, depending on how you want to interpret it. Because if the comet was already magnitude 7 on September 11th, one day before perihelion, that means it had been brightening for weeks, maybe months, as it fell toward the Sun. And during that time, while it was getting brighter, while it was developing a coma and a tail, nobody at NASA, nobody at ESA, nobody monitoring SOHO data in any professional capacity flagged it. September 13th and 14th, 2 days after discovery. And here's where the timeline gets strange. I've searched for professional observation reports from these dates. I've checked the Minor Planet electronic circulars, the repository where confirmed observations are logged. I've looked through astronomy forums, preprint servers, Twitter posts from professional astronomers, and I've found almost nothing. A handful of amateur observations, magnitude estimates ranging from 7 to 6.5. Tail length reports suggesting it might be growing, but no technical analysis, no spectroscopy, no high-resolution imaging, no papers, even preliminary ones, discussing the comet's composition or orbit. Radio silence from the professionals. September 15th, 4 days after discovery. The first detailed amateur brightness estimates start appearing. Observers in the southern hemisphere, where the comet is better positioned in the pre-dawn sky, report magnitude 7, maybe magnitude 6.8. The tail is now estimated at 2 to 3 degrees long, visible in long exposure photographs. But still, nothing from NASA, nothing from ESA, no press release, no update on the SOHO mission page beyond a brief mention that a new comet has been discovered. And then we hit the gap. September 16th through September 21st, 6 days. During this period, something changed, something significant. But if you search for public explanations, for papers or technical notes, or even forum posts from professional astronomers detailing what they observed during these 6 days, you won't find much. What you will find, if you dig through amateur observation reports and Reddit threads from late September, is that predictions for the comet's peak brightness were revised. Dramatically. Initial estimates, based on the comet's brightness at discovery and standard cometary brightening models, suggested it might reach magnitude 5 or 6 at best when it made its closest approach to Earth on October 20th. Magnitude 5 or 6 would make it visible in binoculars under good conditions, interesting for amateur astronomers, but not spectacular. Not a naked-eye comet that casual observers would notice. But by September 22nd, just 11 days after discovery, those predictions had changed. Magnitude 4, some astronomers were saying. Maybe magnitude 3.5 if the current trend continued. That's not a small revision. That's a full magnitude, possibly more. And each magnitude represents a factor of about 2.5 in brightness. So a shift from magnitude 5 to magnitude 4 means the comet is now expected to be 2.5 times brighter than originally thought. A shift to magnitude 3.5, nearly 4 times brighter. So what happened between September 15th and September 22nd? What data came in? What observations were made? What analysis was performed that caused such a dramatic change in brightness predictions? I don't know. And here's the problem. Neither does anyone else who isn't part of the inner circle of professional comet researchers. Because no explanation was published, no paper, no technical note in the Minor Planet electronic circulars, no blog post from a professional astronomer saying, here's what we observed, here's why the models were wrong, here's the new prediction. Just a quiet update to the brightness forecasts. And amateur astronomers on forums scratching their heads, asking, why did the prediction change? What did we miss? Now, let me be clear. Comet brightness predictions are notoriously difficult. Comets are unpredictable. They can have outbursts, sudden surges in activity that cause temporary brightening. They can fragment, breaking apart and releasing fresh ice that dramatically increases outgassing. Their brightening curves don't always follow the simple models based on distance from the sun and the inverse square law of light. So revisions happen. That's normal. But what's not normal is revising a prediction by a full magnitude or more without publicly explaining why. Unless there's something about the observations from September 15th through September 22nd that the professionals don't want to discuss yet, or don't understand yet, or haven't figured out how to explain yet. September 22nd. The revised predictions are now circulating in amateur astronomy communities. Magnitude 4, maybe 3.5. Naked eye visibility likely. Possibly one of the brightest comets in years. And still, no official announcement from NASA or ESA. No press release saying, hey, there's a bright comet coming. Here's when to see it. Here's how to find it. Compare this to how other recent comets were handled. When Comet C 2020 F3 Neowise was discovered in March 2020, NASA started talking about it within weeks. By the time NEOWISE became visible to the naked eye in July, there were observation guides, press releases, social media posts, interviews with astronomers explaining the science. The public was engaged. Millions of people went outside to look. NEOWISE became one of the most photographed comets in history. When Comet C 2022 E3 ZTF was discovered in March 2022 and predicted to reach naked eye brightness in early 2023, NASA put out information. Not as much as NEOWISE, but enough. A press release, some updates on the website, enough that space enthusiasts knew it was coming. But SWAN? Nothing. 28 days after discovery, as of October 9th, 2025, NASA's Near-Earth Object Program website has zero dedicated content about this comet. No press release, no observation guide, no public outreach. The SOHO mission page has a brief mention, a couple of sentences, confirming the discovery, but providing no technical details, no brightness forecasts, no advice for observers. Why? Is it caution? Are they worried about overhyping a comet that might not meet expectations, the way ISON disappointed in 2013? Possibly. ISON was predicted to be spectacular, potentially visible in daylight. Instead, it disintegrated as it passed the sun, leaving behind only a faint debris cloud. NASA took criticism for the hype, and maybe they've overcorrected, deciding to stay silent unless and until a comet definitively proves it's worth talking about. But here's the problem with that theory. SWAN has already proven it's worth talking about. It's magnitude 6 as of October 9th, already visible in binoculars, with a tail stretching 5 to 6 degrees across the sky. That's 10 to 12 full moon diameters. That's a tail visible to the naked eye under dark skies, stretching across a noticeable portion of the heavens. This isn't a marginal object that might or might not reach visibility. This is already visible, already impressive, already worthy of public engagement. And yet, silence. September 25th through September 30th. More amateur observations. The tail continues to grow. By September 28th, some observers are reporting 4 degrees. By October 3rd, over 5 degrees. The brightness is now consistently estimated at magnitude 6 to 6.5, right on the threshold of naked eye visibility. And still, nothing from NASA or ESA beyond the minimal acknowledgement that the comet exists. October 3rd, 22 days after discovery. The tail exceeds 5 degrees. That's confirmed by multiple independent observers in different locations with different equipment. Long exposure photographs show a clear, well-defined tail stretching across the sky. Some observers report faint structure in the tail, possibly a helical or corkscrew pattern, suggesting the nucleus is rotating and releasing jets of gas and dust from active regions on its surface. If true, that's scientifically interesting. That's the kind of detail that could tell us about the nucleus size, rotation period, and distribution of volatile ices. That's data worth analyzing, worth discussing, worth sharing with the public as part of the larger story of what this comet is and how it behaves. But where are the professional observations? Where's the spectroscopy that could confirm the composition? Where's the high-resolution imaging from Hubble or ground-based telescopes that could resolve the nucleus and measure the jets? As far as I can find, none of that data has been released. And if it's been collected, it's being held for later publication months from now in a peer-reviewed journal, behind a paywall, accessible only to academics and institutions with subscriptions. October 7th through October 8th. Something changes. After nearly 4 weeks of silence, ESA finally posts an update on the SOHO mission page. It's brief, 4 sentences, no technical details, just a confirmation that the comet was discovered using SOHO data, that it's currently visible, and that it's behaving as expected. Behaving as expected. Based on what? Expected by whom? What models are being used to determine what's expected? And if the comet is behaving as expected, why were the brightness predictions revised so dramatically between September 15th and September 22nd? The update doesn't answer these questions. It doesn't provide data. It doesn't give observers any new information. It's a minimal acknowledgement, released 26 days after discovery, with just 13 days remaining until closest approach. And the timing is interesting, because on October 7th and 8th, amateur observers started reporting something unusual. Brightness estimates coming in at magnitude 5.5, possibly as bright as magnitude 5.3. That's a noticeable jump from the magnitude 6 to 6.5 estimates from just days earlier. That's the comet brightening faster than even the revised prediction suggested. Is that why ESA finally posted something? Did the rapid brightening prompt a response? I need to acknowledge publicly that yes, the comet exists. Yes, we're aware of it. No, there's nothing to worry about. Or is the timing coincidental? I don't know. And the 4-sentence update from ESA doesn't tell me. October 9th, 2025. Today, 28 days after discovery, 11 days until closest approach, and the silence from the major institutions continues. NASA's Near-Earth Object Program. Nothing. ESA beyond that brief 4-sentence update. Nothing. Hubble Space Telescope observation schedule. I've checked. It's publicly available, though dense and technical. I can't definitively determine whether Hubble has observed SWAN, but there are no publicly released images. No press release announcing Hubble observations. No spectroscopic data shared with the community. James Webb Space Telescope. Same situation. JWST has observed comets before. It's ideal for infrared spectroscopy of cometary volatiles. But as far as I can find, no JWST data on SWAN has been released. Ground-based observatories. Keck, the Very Large Telescope, Gemini, Subaru, all of them capable of detailed comet observations, all of them capable of spectroscopy, photometry, high-resolution imaging. And as far as I can find, no publicly shared results. Now, to be fair, observations take time to process. Data reduction, calibration, analysis, that doesn't happen instantly. And professional astronomers don't just post raw data on Twitter. They write papers. They submit to journals. They go through peer review. That process takes months. But we're not asking for a peer-reviewed paper. We're asking for a press release, an observation guide, a few paragraphs on a website saying, here's a comet, here's where it is, here's how bright it might get, here's how to see it. That doesn't require peer review. That's public outreach. That's what NASA and ESA are supposed to do, and they're not doing it. So we're left with a timeline that raises more questions than it answers. September 11th, discovery. September 12th, confirmation in 17 hours. September 13th and 14th, almost no professional observations reported. September 16th through 21st, the gap, the week when something changed, but nobody explained what. September 22nd, brightness predictions revised upward by a full magnitude. October 3rd, tail exceeds 5 degrees. October 7th and 8th, ESA posts a minimal update, possibly prompted by rapid brightening. October 9th, today, still no comprehensive information from NASA. And in 11 days, on October 20th, this comet will reach its closest approach to Earth. It will be at its brightest. Its tail will be at maximum extension. And the timeline, the data gap, the institutional silence, all of it will still be unexplained. Unless something changes. Unless NASA or ESA decides to finally talk about what they've been observing, what they've been measuring, what they know that we don't. But based on 28 days of silence, I'm not holding my breath. The gap remains. The questions accumulate, and the comet keeps brightening. Let's talk about probability. September 11th, 2025. A comet is discovered in SOHO coronagraph imagery, hidden behind the glare of the sun, already magnitude 7, already developing a tail, already 1 day away from perihelion. What are the odds of that? Not the odds of a comet existing. Comets exist, thousands of them. The Oort cloud, that vast spherical shell of icy bodies surrounding our solar system at distances of tens of thousands of astronomical units, contains trillions of comets. Occasionally, gravitational perturbations send one falling inward toward the sun. That's normal. That's how long-period comets work. But what are the odds of a comet being discovered by an amateur astronomer reviewing publicly available SOHO data at magnitude 7, 1 day before perihelion, when it's been brightening for months and should have been detected much earlier by professional sky surveys? Let's work through the numbers. SOHO's SWAN instrument has discovered comets before. 20 comets, to be precise, according to Vladimir Bezugliy himself. But most of those discoveries were sun grazers, small, faint objects diving into the sun, visible only in the coronagraph because they were so close to solar glare that ground-based telescopes couldn't see them. Objects that would never become bright enough for amateur observation. Objects that existed for a few hours or days before being vaporized. C 2025 R2 SWAN is not a sun grazer. Its perihelion, its closest approach to the sun, was 0.5 astronomical units. That's 75 million kilometers. For reference, Mercury orbits at an average distance of 0.39 AU. So SWAN passed the sun farther out than Mercury, not close enough to be destroyed, not close enough to require a coronagraph for detection. So why was it discovered in a coronagraph? Because it was hidden. Because from Earth's perspective, in early September 2025, the comet was less than 30 degrees from the sun in the sky. And anything within 30 degrees of the sun is effectively invisible to ground-based telescopes. Not because the telescope can't see it, but because the sky is too bright. Daytime sky. The sun's glare overwhelms everything. This is called the Holacek effect, named after the astronomer who first documented it. Comets can brighten dramatically when they're near the sun, heated by intense solar radiation, releasing massive amounts of gas and dust. But if that brightening happens when the comet is too close to the sun in the sky, we can't see it from Earth. It's lost in the glare. SWAN was in that blind zone from August 7th through September 13th, 5 weeks. During that time, it brightened from magnitude 11 to magnitude 8. 4 magnitudes. That's a brightness increase of about 40 times. 40 times brighter over 5 weeks. And nobody saw it. Because nobody could see it. Because it was hidden behind the sun. Except, that's not entirely true. Space-based telescopes don't have to contend with Earth's day-night cycle. They're above the atmosphere. They can observe in directions ground-based telescopes can't. And there are space telescopes specifically designed to monitor the sun and its surroundings. SOHO, obviously. But also Stereo A, the Solar Terrestrial Relations Observatory. Stereo A is positioned ahead of Earth in its orbit around the sun, giving it a different vantage point, a different perspective on the space near the sun. And according to the data I've found, Stereo A did observe SWAN in August, while it was still faint, magnitude 11 or dimmer. But those Stereo A observations weren't flagged as a comet discovery. They were just data points, pixels in an image, low spatial resolution, about 1 degree per pixel, not detailed enough to immediately identify the object as a comet without additional analysis. So the data existed in August, before Vladimir Bezugly's September 11th discovery. But nobody connected the dots. Nobody realized what they were looking at until an amateur astronomer reviewed these SOHO images and said, "That's a comet." Now here's the probability question. What are the odds that an amateur finds a comet in publicly available space telescope data before professionals do? Hard to quantify precisely, but let's estimate. SOHO data is publicly available, yes, but reviewing it systematically requires time, expertise, and persistence. There are thousands of amateur astronomers worldwide, and some of them regularly review SOHO imagery, specifically looking for comets. It's a hobby, a passion, the thrill of discovery. But there are also professional astronomers whose job includes monitoring SOHO data. NASA employs people for this. ESA employs people for this. Not full-time SOHO data reviewers necessarily, but scientists who have access to the data and the responsibility to flag anything interesting. So in a race between hundreds of amateurs worldwide and dozens of professionals with institutional resources, who finds the comet first? In this case, an amateur, Vladimir Bezugliy, on September 11th, 1 day before perihelion. Statistically, I'd estimate the probability of an amateur beating professionals to a discovery like this at maybe 1 in 50, maybe 1 in 100. It happens occasionally, but it's not common. Professionals have advantages: automated detection algorithms, institutional continuity, funding. But amateurs have numbers, distributed observation networks, and sometimes, just sometimes, they notice something first. So let's say 1 in 50 for amateur first discovery. Now, what about the timing? What are the odds that a comet is discovered 1 day before perihelion? Comets are typically discovered months or years before perihelion, when they're still faint, still far from the sun, gradually brightening as they approach. Early detection gives astronomers time to study them, track their orbits, predict their brightness, coordinate observation campaigns. But SWAN wasn't discovered months before perihelion. It was discovered 1 day before, on September 11th. Perihelion, September 12th. Why? Because it was hidden in the sun's glare during its approach. It emerged from that blind zone just in time for discovery, literally hours before reaching its closest point to the sun. That's not impossible, but it's rare, and it means we missed the entire approach phase. We missed watching the comet brighten from magnitude 15 or 20 down to magnitude 11, then to 8, then to 7. We only saw it when it popped out of the solar glare, already active, already bright, already 1 day from perihelion. So what's the probability of discovering a comet 1 day before perihelion, specifically because it was hidden in solar glare? Let's estimate 1 in 20, maybe 1 in 30. Most comets aren't perfectly aligned with the sun during their approach. Most are visible for months before perihelion. But occasionally, orbital geometry conspires to hide a comet until the last moment. Multiply those probabilities. Amateur discovery, 1 in 50. Discovery 1 day before perihelion, 1 in 25. Combined, 1 in 1,250. Not impossible, but uncommon. And that's before we factor in everything else. Now let's talk about the brightness curve. Between August 7th and September 13th, SWAN brightened from magnitude 11 to magnitude 8, according to the reconstruction from stereo A data. That's reasonable. Comets brighten as they approach the sun. Standard physics. Solar radiation heats the nucleus. Ice sublimates. Gas and dust are released. Brightness increases. But then, between September 13th and September 16th, something unusual happened. The comet brightened from magnitude 8 to magnitude 6.2. 2 magnitudes in 3 days. That's a brightness increase of about 6 times in 72 hours. Was that an outburst? A sudden surge in activity, a temporary increase in outgassing driven by the exposure of fresh volatile ice, or a subsurface pocket of gas suddenly venting into space? Possibly. Cometary outbursts happen. They're not rare, but they're also not typical for a comet just past perihelion, when outgassing should be stabilizing, not surging. Or was it gradual brightening that we simply didn't observe until September 16th, because the comet was still emerging from solar glare? Also possible. We don't have continuous observation data for those 3 days. We have spotty amateur reports, magnitude estimates from different observers using different equipment under different conditions. So maybe the comet didn't surge from magnitude 8 to 6.2. Maybe it was already magnitude 7 or 6.5 on September 13th, and we just didn't have good enough observations to confirm it. But here's what makes this suspicious. On September 22nd, 11 days after discovery, brightness predictions for October 20th, the date of closest approach to Earth, were revised upward from magnitude 5 to 6 to magnitude 4, possibly 3.5. Why? What changed between September 11th and September 22nd that caused a full magnitude upward revision in the peak brightness forecast? I've searched for an explanation. I've checked preprint servers, technical notes, astronomy forums, anywhere a professional astronomer might have posted an analysis explaining the revision. Nothing. No published explanation. Just a quiet change in the numbers. So let's speculate. What could cause a magnitude 4 comet prediction to be revised from initial estimates of magnitude 5-6? Larger nucleus. If the comet's nucleus is bigger than initially estimated, more surface area means more ice, more outgassing, more brightness. Initial estimates might have assumed a nucleus diameter of 1 to 2 kilometers based on the observed brightness at discovery. But if the nucleus is actually 3 or 4 kilometers across, that would explain higher brightness. Unusual composition. If the comet is richer in volatile ices, carbon monoxide, methane, nitrogen, substances that sublimate at lower temperatures and drive more vigorous outgassing than water ice, that would explain faster brightening and higher peak brightness. Continued outburst activity. If the comet experienced an outburst around September 16th and continued to show elevated activity in the days following, that would suggest sustained higher than expected outgassing, justifying a brighter peak prediction. Or something else, something unexpected, something that doesn't fit the standard models and that professionals don't want to speculate about publicly until they have more data. But here's the problem. We're not speculating anymore. We're 11 days from closest approach. The comet is magnitude 6 as of October 9th. In 11 days, on October 20th, we'll know if it reaches magnitude 4, or exceeds it, or falls short. And if it exceeds magnitude 4, if it climbs to magnitude 3 or brighter, that's not just brighter than the revised prediction. That's significantly brighter. That's one of the brightest comets in years. Visible not just from dark rural locations, but from suburban areas, maybe even cities with moderate light pollution. That would be news. That would be something NASA should be preparing the public for. Observation guides, press releases, social media campaigns. Look up, there's a bright comet coming. Here's when and where to see it. But they're not doing that, because maybe they don't know if the comet will reach magnitude 4. Maybe they're waiting to see. Maybe they've been burned before by overhyping comets that underperformed, and they've decided to stay cautious, stay silent, until the comet proves itself. Or maybe they know something we don't. Maybe observations from professional telescopes, observations that haven't been released publicly, show something unusual, something they're still trying to interpret. Now let's talk about the tail. As of October 3rd, 22 days after discovery, the tail exceeded 5 degrees in length. By October 9th, some observers report 6 degrees, maybe more. That's 10 to 12 full moon diameters stretching across the sky. For a comet discovered 28 days ago, that's rapid tail development. Most comets take months to grow tails that long. SWAN did it in less than 4 weeks. Why? High outgassing rate. If the nucleus is releasing large amounts of gas and dust, driven by intense solar heating and abundant volatile ices, the tail would grow quickly. That's consistent with the brightening curve. Fast brightening plus rapid tail growth both point to a highly active comet. But here's where the numbers get interesting. The tail isn't just long. It has structure. Some observers report a faint helical or corkscrew pattern visible in long exposure photographs. That kind of structure forms when the nucleus is rotating and releasing jets of gas and dust from localized active regions. As the nucleus spins, the jets trace out a spiral pattern. If that structure is real and not just a processing artifact or pareidolia, it tells us something about the rotation period. A well-defined helical structure suggests a rotation period on the order of hours to days. Fast enough to create the spiral, slow enough that the pattern is visible rather than smeared out. But we don't have spectroscopy. We don't have photometric light curves tracking brightness variations over time. We don't have high-resolution imaging showing the nucleus. All we have are amateur photographs showing structure in the tail that might be real or might be noise. And the professionals? They're not talking about it. Now, the final number, the one that really doesn't make sense. October 20th, 2025. Closest approach to Earth. Distance, 0.26 astronomical units. That's 39 million kilometers, roughly 24 million miles. Compare that to other close comet approaches. Comet Neowise in July 2020 passed Earth at 0.69 AU. Comet Hale-Bopp in 1997 passed at 1.32 AU. Comet Hyakutake in 1996, one of the closest comet approaches in modern history, passed at 0.10 AU. So SWAN at 0.26 AU is closer than Neowise. Not as close as Hyakutake, but closer than most bright comets in recent decades. Close enough for excellent observation. Close enough that even modest amateur telescopes will show significant detail. And yet, we didn't know this comet existed until 39 days before closest approach. Think about that. 39 days. Most near-Earth objects, asteroids or comets, are detected months or years before they pass Earth. NASA's Near-Earth Object Program tracks these things. That's their mandate. Find them early. Characterize them. Make sure nothing dangerous slips through unnoticed. And a comet passing at 0.26 AU, bright enough to potentially reach magnitude 4, was discovered 39 days before closest approach by an amateur, reviewing publicly available data. The probability of that? I don't know how to calculate it, but it's low, uncomfortably low. So we're left with a comet that was discovered by an amateur one day before perihelion, that brightened faster than models predicted, that developed a 6-degree tail in less than a month. that will pass Earth at 0.26 AU on October 20th, and that has received almost no institutional attention from NASA or ESA despite all of this. The numbers don't make sense, or they make perfect sense, and we're just not being told why. 11 days until closest approach. The numbers will either confirm the predictions, or they'll reveal something unexpected. And based on everything so far, I'm not confident the predictions are right. 28 days. That's how long it's been since Vladimir Bezugliy discovered C 2025 R2 SWAN. 28 days since September 11th. 28 days of watching this comet brighten from magnitude 7 to magnitude 6. Watching its tail grow from 2 degrees to 6 degrees. Watching amateur astronomers around the world photograph it, track it, share observations. And in those 28 days, here's what NASA has published. 2 astronomy picture of the day features. September 16th, September 18th. Both written by professional astronomers Robert Nemiroff and Jerry Bonnell. Both beautiful. Both providing basic observational details. Comet discovered by Vladimir Bezugliy, visible with binoculars, currently in southern skies, will make closest approach to Earth on October 20th. That's it. No press release from NASA headquarters. No statement from the Near-Earth Object Program at JPL. No observation guide on the NASA website. No social media campaign from NASA's official accounts. No educational content explaining what long-period comets are, why this one is interesting, how to observe it. Just 2 APOD features, standard daily content, the kind of thing NASA does for dozens of astronomical events throughout the year. For a comet that's potentially the brightest in years, that was discovered just 39 days before its closest approach to Earth, that's been visible in binoculars for nearly a month. That's all NASA has said publicly. Why? Let's compare this to how NASA handled other recent comets, because the contrast is striking. Comet C 2020 F3 NEO-WISE, discovered March 27, 2020, by NASA's NEO-WISE Space Telescope. Initially faint, predicted to brighten as it approached the Sun in early July. By mid-June, NASA was already talking about it. Press releases, updates on the NASA website, social media posts encouraging people to watch for it. When NEO-WISE reached peak brightness in July 2020, becoming easily visible to the naked eye even from cities, NASA went all in. Daily updates, observation guides, live streams from observatories, interviews with astronomers, educational content explaining cometary science, hashtags trending on social media. NEO-WISE became a cultural moment. Millions of people went outside to see it. It was photographed from every continent. It appeared in news coverage worldwide. NASA facilitated that. NASA promoted it. NASA made sure the public knew this was happening and why it mattered. Comet C 2022 E3 ZTF, discovered March 2, 2022, by the Zwicky Transient Facility at Palomar Observatory, predicted to reach naked eye brightness in early 2023. NASA didn't promote this one as aggressively as NEO-WISE, but they did promote it. Press releases in late 2022. Articles on NASA's website in January 2023. Social media posts with observation tips. Enough public engagement that space enthusiasts knew it was coming. But SWAN? Nothing beyond the 2 APOD features. Why the difference? One possibility: caution after ISON. Comet C 2012 S1 ISON, discovered September 21st, 2012, more than a year before its November 2013 perihelion. Initial predictions suggested it could become spectacularly bright, possibly visible in daylight, potentially the comet of the century. NASA hyped it. Media hyped it. The public was primed for a spectacular show. And then ISON disintegrated. As it passed within 1.2 million kilometers of the Sun, tidal forces and intense heating tore it apart. What emerged from perihelion wasn't a bright comet. It was a faint cloud of debris. The comet of the century fizzled. NASA took criticism for that, for overhyping an event that didn't deliver, for getting the public excited about something that ultimately disappointed. Maybe that burned them. Maybe they decided to be more cautious going forward. Don't hype a comet until it proves itself. Don't promise spectacular displays that might not materialize. Wait and see. That's a reasonable strategy. Comets are unpredictable. Better to underpromise and overdeliver than the reverse. But here's the problem with that explanation. SWAN has already proven itself. It's not a marginal prediction anymore. It's magnitude 6. Visible with binoculars. Tail stretching 6 degrees. Already impressive. Already worth observing. This isn't a situation where NASA is being cautious about a comet that might become bright. This is a comet that is bright. Right now. Today. And NASA is still saying almost nothing. Another possibility. Resource constraints. NASA is a large organization with limited budgets and competing priorities. Right now, in October 2025, NASA is focused on the Artemis program, on returning humans to the moon, on the James Webb Space Telescope's ongoing observations, on Mars sample return, on dozens of other missions, projects, and scientific endeavors that require funding, personnel, and public communication bandwidth. Maybe a newly discovered comet, even a bright one, just doesn't rank high enough on the priority list to warrant a dedicated press campaign. Maybe NASA's public affairs office is stretched thin, and comet outreach falls through the cracks. That's plausible. But it's also disappointing, because one of NASA's core functions, one of the things Congress funds them to do, is public engagement. Education. Inspiring the next generation of scientists and engineers. Connecting people to the wonder of space exploration. A bright comet, visible without specialized equipment, accessible to anyone with binoculars in a dark sky, is exactly the kind of event that NASA should be promoting. It's an opportunity, a chance to get people looking up, thinking about the cosmos, engaging with astronomy in a direct, tangible way, and they're not taking it. Now let's talk about what NASA hasn't released, because the absence of certain types of data is as conspicuous as the absence of press releases. Hubble Space Telescope observations. Hubble has observed comets before, dozens of them. It's capable of resolving cometary nuclei, measuring rotation rates, detecting jets and active regions, tracking changes in brightness and morphology over time. Has Hubble observed SWAN? I don't know. Hubble's observation schedule is publicly available, but it's dense, technical, coded in ways that require insider knowledge to parse. There are entries for target coordinates, instrument configurations, exposure times, but without knowing exactly where SWAN was on specific dates and which observation program corresponds to which target, I can't definitively say whether Hubble has pointed at this comet. But here's what I can say. As of October 9th, 28 days after discovery, there are no publicly released Hubble images of SWAN, no press release announcing Hubble observations, no technical papers using Hubble data. If Hubble has observed this comet, that data is being held for later publication, likely months from now. James Webb Space Telescope observations. JWST is ideal for cometary science. Its infrared instruments can detect water vapor, carbon monoxide, carbon dioxide, methane, all the volatiles that make comets active. It can measure outgassing rates, track changes in composition as different ices sublimate, provide insights into the chemical makeup of material from the outer solar system. Has JWST observed SWAN? Again, I don't know. And again, as of October 9th, no publicly released JWST data, no images, no spectra, no press release announcing observations, ground-based spectroscopy, professional observatories, Keck in Hawaii, the Very Large Telescope in Chile, Gemini, Subaru. All of them have spectrographs capable of analyzing cometary composition. Point a spectrograph at a comet, capture its light, break that light down into its component wavelengths, and you get a chemical fingerprint. You can identify which gases are being released, in what abundances, and how that changes over time. This is routine comet observation. It doesn't require cutting-edge technology or special allocations of telescope time. It's standard procedure. And yet, as far as I can find, there's no publicly available spectroscopic data for SWAN. No papers on preprint servers. No observation reports in the Minor Planet Electronic Circulars detailing composition measurements. Nothing. Either these observations haven't been made, which would be surprising given the comet's brightness and accessibility, or they have been made and the data is being held for peer review and formal publication months from now. Either way, the public doesn't have access. Amateur astronomers tracking this comet, trying to understand what it's made of and why it's behaving the way it is, don't have access. We're left guessing. Now let's talk about ESA, the European Space Agency. Because SOHO, the spacecraft that provided the imagery leading to SWAN's discovery, is a joint NASA-ESA mission. ESA has just as much stake in this as NASA, maybe more, since their spacecraft enabled the discovery. And yet ESA's response has been similarly muted. On October 7th, 26 days after discovery, ESA posted a brief update on the SOHO mission page. 4 sentences. Comet C 2025 R2 SWAN was discovered September 11th using SOHO SWAN instrument imagery, currently visible with binoculars, making closest approach to Earth October 20th, behaving as expected. That's it. No technical details, no brightness measurements, no explanation of what behaving as expected means, no observation guide for European sky watchers, no social media campaign promoting the discovery, just 4 sentences, a minimal acknowledgement, released with 13 days remaining until closest approach. Why the delay? Why wait 26 days to acknowledge the discovery when amateurs found it within hours and the Minor Planet Center confirmed it within 17 hours? Maybe ESA was waiting to see if the comet would live up to its initial promise. Maybe they were being cautious, not wanting to hype something that might fizzle. But again, the comet has proven itself. Magnitude 6, 6-degree tail, clearly worth talking about. And yet ESA waited until October 7th to say anything beyond the standard APOD features. Here's what strikes me as most suspicious. The coordination, or rather, the lack of coordination that looks like coordination. NASA and ESA don't always move in lockstep. They're separate agencies with separate priorities, separate budgets, separate public affairs strategies. Sometimes, NASA announces something, and ESA follows days later. Sometimes, ESA goes first. Sometimes they issue joint statements. It varies. But with SWAN, both agencies have been similarly quiet. Both have published minimal information. Both have avoided detailed technical releases. Both have held back spectroscopy, high-resolution imaging, compositional analysis. That could be coincidence. Or it could be something else. Because here's the thing. When 2 independent organizations with different institutional cultures and different approaches to public communication both stay quiet about the same event at the same time. That's notable. That's a pattern. It suggests either shared caution, both waiting to see how the comet performs before committing to public statements, or shared knowledge, both aware of something about this comet that they're not ready to discuss publicly. I don't know which, but the parallel silence is conspicuous. Now let's talk about what this silence creates, what it enables. In the absence of authoritative information from institutions, people speculate. They fill the vacuum with theories, questions, suspicions, and social media amplifies that. Reddit threads asking, "Why isn't NASA talking about this?" Hundreds of upvotes, dozens of comments, people wondering if there's something unusual about the comet that NASA doesn't want to admit. People comparing SWAN to past comets and noting the difference in institutional response. People sharing amateur observations and pointing out discrepancies with the official predictions. Twitter posts, or X posts now, from amateur astronomers saying, "I'm seeing magnitude 5.8, but the official estimate is 6.3. Why the difference?" Other users reply with speculation. Maybe the official estimates are out of date. Maybe the comet is brightening faster than models predict. Maybe there's something NASA isn't telling us. YouTube videos analyzing the timeline, pointing out the data gap, questioning why professional observatories haven't released spectroscopy. Some of these videos veer into conspiracy territory. NASA is hiding the truth about SWAN. This comet is behaving strangely, and they don't want us to know. That's where it gets irresponsible. That's where speculation crosses into misinformation. But here's the thing. The speculation wouldn't happen if NASA and ESA provided clear, timely information. If there were regular updates, observation data, technical notes explaining the comet's behavior, the vacuum wouldn't exist. The questions would be answered. Instead, the silence creates space for doubt, for mistrust, for the sense that something is being hidden, even when the reality is probably more mundane. Probably just bureaucratic slowness, institutional caution, resource constraints. But people don't assume mundane explanations when institutions stay silent. They assume cover-up. They assume something's being withheld. And that assumption, justified or not, erodes trust. So why isn't NASA talking? Maybe caution after ISON. Maybe resource constraints. Maybe waiting for peer review before releasing data. Maybe coordinating with ESA on a joint statement that's taking longer than expected to finalize. Or maybe, just maybe, there's something about this comet's observations, something in the spectroscopy, or the high-resolution imaging, or the photometric data, that doesn't fit expectations. Something unusual enough that professionals want to verify it, triple-check it, make absolutely certain before saying anything publicly. Because once you say, "This comet is behaving in ways we don't understand," you can't unsay it. Once you admit uncertainty, the speculation intensifies. So maybe silence, frustrating as it is, feels safer than premature disclosure of anomalies that might turn out to have mundane explanations. I don't know. And that's the problem. 28 days after discovery, with 11 days until closest approach, we're still guessing, still waiting, still watching a comet that's brightening and growing and approaching, with almost no guidance from the institutions whose job it is to guide us. The silence continues, and in 11 days, on October 20th, SWAN will either meet expectations or it won't. And NASA will either have an explanation ready or they won't. But based on 28 days of minimal communication, I'm not confident we'll get answers even then. Here's what we've been told. Comet C 2025 R2 SWAN is a long-period comet with an orbital period of approximately 1,400 years. Its last appearance in the inner solar system was around the year 625 CE, give or take a few decades, during the reign of Emperor Heraclius in Byzantium. The early days of the Tang dynasty in China, the time when the Prophet Muhammad was consolidating the Islamic community in Arabia. 1,400 years ago, this comet passed through the inner solar system, developed a tail, became visible from Earth, and then departed, climbing back out into the darkness beyond Neptune, beyond the Kuiper Belt, all the way to the Oort cloud. And now it's back. Except, maybe it's not. Because when you dig into the orbital calculations, when you examine the data carefully, when you compare what different sources are saying, a different picture emerges. A confusing picture. A picture that suggests the 1,400 year period might be wrong. Let's start with what Wikipedia says. As of October 8, 2025, Wikipedia's article on C 2025 R2 SWAN states the comet's aphelion, its farthest point from the Sun, at 150 plus or minus 11 astronomical units. Orbital period, 654 plus or minus 70 years. 654 years, not 1,400. That's a massive discrepancy, more than half. If the true period is 654 years, then the comet's last appearance wasn't in 625 CE. It was around 1371 CE, the late Middle Ages, the time of the Ming Dynasty in China, the early Renaissance in Europe, a period with much better astronomical records than the 7th century. And its next appearance wouldn't be in the year 3425. It would be around 2679. Still far in the future, but dramatically closer. So which is it? 1,400 years, or 654 years? The answer, frustratingly, is that we don't know with certainty. And the reason we don't know is because calculating the orbital period of a long-period comet discovered near perihelion is extraordinarily difficult. Here's why. To determine a comet's orbit precisely, you need observations spread out over as much of the orbit as possible. Ideally, you'd track the comet for years, watching it move against the background stars, measuring its position at regular intervals as it travels from perihelion back out toward aphelion. But with SWAN, we don't have that luxury. The comet was discovered on September 11th, one day before perihelion. As of October 9th, we have 28 days of observations. 28 days out of an orbit that takes centuries. That's an observation arc of less than 1/10% of the total orbital period. Calculating an accurate orbit from such a short arc is like trying to determine the shape of a racetrack by watching a car drive past you for 3 seconds. You can make estimates. You can extrapolate. But your uncertainty is enormous. And that uncertainty shows up in the numbers. Aphelion, 150 plus or minus 11 AU. That plus or minus range represents the uncertainty. The comet's farthest point from the Sun could be as close as 139 AU, or as far as 161 AU. And that 22 AU spread translates to a huge uncertainty in the orbital period. At 139 AU, the period might be around 580 years. At 161 AU, closer to 730 years. The Wikipedia value of 654 plus or minus 70 years encompasses that range. But where does the 1,400 year estimate come from? It comes from earlier, less refined calculations. In the days immediately after discovery, when observers had only a handful of position measurements, the orbital elements were poorly constrained. Some early estimates suggested an aphelion of 200 AU or more, which would correspond to a period of 1,000 to 2,000 years. As more observations came in, those estimates were refined. The aphelion moved inward, the period shortened, and now, as of October 9th, the best available estimate is around 654 years. But here's the problem. That estimate depends critically on observations from Stereo A, the Solar Terrestrial Relations Observatory spacecraft. Stereo A imaged the region where SWAN was located back in August 2025, before the comet was discovered. Those images, with their low spatial resolution of about 1 degree per pixel, provided pre-covery data, observations of the comet before anyone knew it was a comet. And those pre-covery observations are what constrain the orbit. Without them, the observation arc would be only 21 days, from September 11th to October 2nd. With them, it extends back to August, giving a 50-day arc. But Stereo A's resolution is terrible. 1 degree per pixel. That's 2 full moon diameters per pixel. Position measurements from those images are imprecise, and imprecise measurements lead to uncertain orbits. So the 654-year period is based on shaky data that might be revised as more observations come in, data that could shift the period up or down by hundreds of years depending on how the orbit is refined. And here's where it gets even more interesting. Some sources are still citing the 1,400-year period. Articles from late September, before the orbit was refined with Stereo A data, still reference it. Forum posts from amateur astronomers discussing historical records of the comet's previous appearance assume 1,400 years. So we have 2 different narratives circulating simultaneously. One says 1,400 years, last appearance 625 CE. The other says 654 years, last appearance 1371 CE. And neither can be definitively confirmed yet. Now let's talk about what this means for historical records. Because if the period is around 1,400 years, we should find references to a bright comet in or around 625 CE. If the period is around 654 years, we should find references around 1371 CE. So do we? For 625 CE, the records are sparse. This was the early 7th century, a period when Europe was deep in the Dark Ages. Literacy was limited to monastic communities. Scientific observation was almost non-existent. Most historical chronicles from this period don't mention astronomical events in detail. But China is different. Chinese astronomers in the 7th century kept meticulous records. Comets were significant omens, signs that required interpretation by imperial astrologers. And those observations were recorded in official dynastic histories. So I went looking. Historical catalogs of Chinese cometary observations, compilations of records from the Tang dynasty, which ruled China from 618 to 907 CE. And what I found was inconclusive. There are records of comets from the early 7th century. Several, in fact, but the descriptions are vague. A comet appeared in the eastern sky. A broom star was seen near the constellation Shen. Observations like that, lacking precise positions, lacking brightness estimates, lacking details that would allow us to match them to a specific comet with a known orbit. One record from 615 CE mentions a comet visible for several weeks in spring. Could that be SWAN? Possibly. The timing is close to the 625 CE estimate, within the uncertainty of the orbital period calculation. But the description doesn't provide enough information to confirm or rule it out. Another record from 637 CE describes a bright comet in autumn. Again, could be SWAN if the period is slightly different than 1,400 years, maybe 1,388 years, which would shift the previous apparition from 625 to 637. But again, the description is too vague for confirmation. Now for 1371 CE. This is a much better documented period. The Ming Dynasty in China had just come to power in 1368. Europe was in the midst of the Renaissance. Astronomical records from this period are more detailed, more systematic, more likely to include the kind of information that would allow us to match historical observations to modern orbital calculations. And there are records, multiple records of comets visible in the late 14th century. 1368, 1369, 1372, 1378. Several bright comets observed and documented. But here's the problem. Without precise positions, without detailed descriptions of the orbits, it's impossible to say which, if any, of these historical comets was SWAN. Comets were common in historical skies, not every year, but frequently enough that multiple bright comets per decade was normal. Trying to match one specific comet to historical records without detailed orbital information is guesswork, so we're left with uncertainty. The period might be 1,400 years. It might be 654 years. It might be somewhere in between. Historical records don't definitively confirm or rule out either possibility, and that raises a question. If we can't even determine the orbital period with confidence, if the uncertainty spans hundreds of years, what else don't we know about this comet? Now let's talk about an alternative theory, one that doesn't get discussed much in official sources, but that circulates in amateur astronomy forums and Reddit threads. What if this is SWAN's first pass through the inner solar system? Not its first orbit around the sun, but its first time coming close enough to the sun to be heated, to develop a coma and tail, to become an active comet. Here's how that would work. SWAN originates from the Oort cloud. It's been out there for billions of years, drifting in a vast, slow orbit at distances of thousands or tens of thousands of AU. Then recently, on a cosmic timescale, something perturbed it. A gravitational nudge from a passing star, from the galactic tide, from another Oort cloud object. That nudge altered the orbit, sending SWAN falling inward. But instead of falling directly into the inner solar system, it first passed through the outer solar system. It came close to Neptune, or Uranus, or Jupiter. And one of those planets, with its massive gravitational field, altered SWAN's orbit again, bringing its perihelion distance down from hundreds of AU to just 0.5 AU, close enough for solar heating to trigger outgassing. If that's the case, then SWAN has never been this close to the sun before. It's a pristine comet, carrying ice that's been frozen and unchanged for 4.6 billion years. And that pristine ice, when exposed to solar radiation for the first time, could produce more vigorous outgassing than a comet that's been through multiple passages and has built up a crust of non-volatile material on its surface. This would explain the rapid brightening. It would explain why the comet seems more active than models predict. Pristine ice sublimates more easily than processed ice. Fresh volatiles drive higher outgassing rates. And it would explain why there are no clear historical records. Because if this is SWAN's first inner system pass, there wouldn't be any. No previous apparitions to document. No 625 CE observation. No 1371 CE observation. This is the first time humans have seen this object. But here's the problem with that theory. The orbital calculations don't support it. Even with the uncertainties, even with the imprecise stereo A data, the orbit looks like a bound ellipse, not a parabolic or hyperbolic orbit that would indicate a first-time visitor. The eccentricity is high, around 0.997, but not quite 1.0, which is what you'd expect for a comet on its first inbound pass. So SWAN has been here before. Probably. Maybe. Unless the orbital elements change as more data comes in, and that's the frustration. 28 days after discovery, we still don't know basic facts about this comet. Is its period 654 years or 1,400 years? Was its last appearance in 1371 or 625? Is it a returning visitor or a pristine first-timer? The professionals aren't clarifying. The data is ambiguous. And the closer we get to October 20th, the more these unanswered questions accumulate. Because understanding where this comet has been tells us what to expect from where it's going. A pristine comet might brighten more dramatically, might fragment more easily, might behave in ways that experienced comets don't. A returning visitor with a 654-year period might be more stable, more predictable, less likely to surprise us. But we don't know which we're dealing with. And with 11 days until closest approach, that uncertainty is becoming a problem. The 1,400-year claim might be wrong. The 654-year revision might also be wrong. We might not know the truth until years from now, when the orbit is refined with long-term tracking data. But October 20th isn't years from now. It's 11 days away. And whatever SWAN does on that date, whether it meets expectations or exceeds them, or fragments or fades, we'll be watching without fully understanding what we're looking at. The historical mystery remains, the orbital uncertainty remains, and the silence from institutions that should be clarifying these things, that remains too. 2 comets, same month, both visible. C 2025 R2 SWAN, discovered September 11th, currently magnitude 6, tail stretching 6 degrees, closest approach to Earth, October 20th. Predicted peak brightness magnitude 4, possibly brighter. C 2025 A6 Lemon, discovered earlier this year, currently magnitude 5 to 6, also visible with binoculars, also approaching peak brightness in mid-October. Predicted magnitude 2 to 4. 2 naked eye comets, same time frame, October 2025. When was the last time that happened? The answer depends on how you define naked eye. If you're generous, if you count comets that are technically magnitude 6, but require perfect dark skies and adapted eyes to see without optical aid, then paired comets happen maybe once every 5 to 10 years. Not common, but not unprecedented. But if you're strict, if you only count comets that are unmistakably visible, magnitude 4 or brighter, clearly distinguishable from background stars without squinting or knowing exactly where to look, then paired comets are rarer. Maybe once every 20 or 30 years, maybe less. The last major example was 1996 and 1997. Comet Hyakutake in March 1996, reaching magnitude 0, one of the brightest comets of the 20th century. Then Comet Hale-Bopp in March and April 1997, visible for over a year, magnitude negative 0.7 at peak, seen by more people than any comet in modern history. But even then, Hyakutake and Hale-Bopp didn't overlap. Hyakutake faded before Hale-Bopp brightened. There was a gap. They were sequential, not simultaneous. SWAN and Lemon are simultaneous, both visible in October 2025, both in the evening sky, though in different parts of the sky, requiring observers to look in different directions. But both there, both accessible, both providing opportunities for observation and photography. So what are the odds of that? Let's estimate. On average, a comet bright enough to be visible to the naked eye, magnitude 6 or better, appears roughly once every 1 to 2 years. Some years have none. Some years have multiple. But 1 to 2 per year is a reasonable average based on historical data. Now, most comets are visible for a few weeks to a few months, depending on their brightness, their trajectory, and how quickly they're moving relative to Earth. Let's say the average visibility window for a naked eye comet is 2 months. If comets appear randomly throughout the year, the probability that 2 comets would both be visible during the same month is low. Not astronomically low, not impossible, but low. Rough estimate, maybe 5 to 10% chance in any given year, which translates to one overlap every 10 to 20 years on average. So SWAN and LEMON appearing together in October 2025 isn't impossible. It's within the range of normal variability, but it's also notable, worth remarking on, worth asking, is this coincidence or is there a pattern? Now let's talk about the orbits, because if SWAN and LEMON are related, if they're fragments of a larger parent body that broke apart at some point in the past, or if they were both perturbed by the same gravitational influence, their orbits should show similarities. So do they? No. SWAN's orbit is inclined 4.5 degrees relative to the ecliptic plane, the plane in which Earth and most planets orbit the Sun. That's unusually low for a long-period comet from the Oort cloud, which typically arrive from random directions with inclinations spread across the full range of 0 to 180 degrees. LEMON's orbit, by contrast, is steeply inclined. I don't have the exact number, but based on its discovery location and trajectory, it's approaching from a very different direction than SWAN. Their perihelion distances are different. SWAN, 0.5 AU. LEMON, I've seen estimates around 0.4 to 0.5 AU, but the exact number depends on which source you consult and how recent the orbital calculation is. Their aphelion distances are different. SWAN, 150 plus or minus 11 AU, according to Wikipedia's October 8th data, or 1,596 AU according to the SkyLive's data, which cites JPL small body database and suggests a 22,005 feet 4-year period, or somewhere in between. The uncertainty is enormous. LEMON's aphelion is less well constrained because it was discovered farther from perihelion, giving a longer observation arc, but still subject to uncertainties. Point is, their orbits don't match. They're not related. They're not fragments of a common parent. They didn't originate from the same region of the Oort cloud. They're independent objects that happen to be passing through the inner solar system at the same time. Coincidence. Except, some researchers aren't entirely convinced it's pure coincidence. Dr. Avi Loeb, the Harvard astrophysicist, who's been making waves with his willingness to consider unconventional explanations for astronomical phenomena, has speculated publicly about whether SWAN and another object, 3I Atlas, an interstellar visitor currently approaching the Sun, might share a common origin. Not SWAN and LEMON, SWAN and 3I Atlas. And while orbital calculations quickly ruled out that idea, the fact that a Harvard professor even raised the possibility speaks to how unusual this clustering of bright comets and interstellar objects feels. Because it's not just SWAN and LEMON. There's also 3I Atlas, an interstellar comet discovered in July 2025, currently approaching its perihelion passage in late October. 3I Atlas isn't as bright as SWAN or LEMON. It's predicted to reach maybe magnitude 8 or 9 at best, requiring telescopes to observe. But it's still there, still part of the October 2025 traffic jam of icy visitors. 3 objects, SWAN, LEMON, 3I Atlas, all approaching the Sun, all visible or detectable in October 2025, all drawing attention from professional and amateur astronomers. That's not normal. That's a statistical outlier. So what's causing it? Theory 1. Pure coincidence. Comets arrive randomly. Sometimes they cluster. Sometimes years pass without any bright comets. This is just one of the years where multiple objects happen to arrive at once. No deeper explanation needed. Randomness clusters. Flip a coin enough times, you'll get 10 heads in a row eventually. This is that. October 2025 just happens to be the month when several independent, unrelated comets showed up simultaneously. Theory 2. Observational bias. Maybe comets aren't clustering. Maybe we're just noticing them more because technology has improved. Automated sky surveys. Space-based telescopes like SOHO and Stereo. Distributed networks of amateur astronomers reviewing public data. We're finding comets earlier, tracking them more carefully, publicizing them more widely. So what looks like a cluster might just be better detection. But that doesn't explain SWAN and LEMON both being bright, both being naked eye objects. Detection bias would increase the number of faint comets we find. It wouldn't make multiple comets independently decide to be bright at the same time. Theory 3. External perturbation. Something is disturbing the Oort cloud. A passing star. A massive rogue planet in the outer solar system. The gravitational influence of the galaxy itself. And that disturbance is sending multiple Oort cloud objects falling inward simultaneously, resulting in increased cometary activity in the inner solar system. This theory has historical precedent. There's evidence that Earth has experienced periods of increased cometary impacts in the past, possibly triggered by Oort cloud perturbations from nearby stars passing within a light year or two of the Sun. Those perturbations send showers of comets inward, and for a few thousand years, the rate of comet arrivals increases. But here's the problem with that explanation. The timescales don't match. Oort cloud perturbations take hundreds of thousands of years to manifest as increased cometary activity. If a star passed close enough to disturb the Oort cloud and send comets raining toward the inner solar system, those comets wouldn't all arrive in October 2025. They'd arrive spread over millennia, unless the perturbation happened recently, within the last few thousand years. And the comets are just now starting to arrive. But that's speculation. There's no evidence of a recent stellar encounter, no observations of a passing star, no anomalies in the orbits of outer solar system objects that would suggest a massive perturber. Theory 4. Planet 9. The hypothetical super-Earth, or mini-Neptune lurking in the outer solar system, proposed to explain clustering in the orbits of distant trans-Neptunian objects. If Planet 9 exists, some models suggest it could perturb the Oort cloud, triggering periodic comet showers. But again, timescales. Even if Planet 9 exists, even if it's perturbing the Oort cloud, the effects would take thousands of years to manifest. You wouldn't see a sudden spike in 2025. Unless Planet 9's orbit brings it close to the Oort cloud in cycles, and we're currently in a phase where that perturbation is maximized. But that's layers of speculation on top of the already speculative existence of Planet 9. So we're left with coincidence. Two bright comets, SWAN and LEMON, both visible in October 2025, both unrelated, both arriving at the same time by chance. And while that's the simplest explanation, while it's almost certainly the correct explanation, it doesn't feel satisfying. Because humans are pattern seekers. We see connections where none exist. We infer meaning from randomness. And when two comets show up in the same month, after years of relatively quiet skies with no bright comets at all, we ask, why now? What's special about October 2025? And the answer, frustrating as it is probably nothing. Nothing is special about October 2025. Comets arrived. That's what comets do. Sometimes they arrive alone. Sometimes they arrive in pairs. This is one of the times they arrived in pairs. But here's what makes the twin comet situation more interesting. The institutional response, or lack thereof. You'd think NASA would be excited about this. Two bright comets, both visible in the same month. both accessible to amateur observers with minimal equipment. That's a public engagement opportunity. That's a chance to get people excited about astronomy, to encourage them to go outside and look up, to connect with the night sky in a tangible way. And yet, as of October 9th, NASA hasn't done much with it. No dedicated observation campaign, no press releases promoting October 2025, Month of the Comets, no social media hashtags, no live streams from observatories showing both comets side by side. ESA? Same. Minimal engagement. The New York Times published an article on October 3rd. 2 comets are moving into your night skies in October. That's mainstream media coverage. That's public awareness. But it's not coming from NASA or ESA. It's coming from journalists covering the story independently. Why aren't the space agencies leveraging this? Why isn't there more institutional enthusiasm for an event that won't repeat for years, maybe decades? Maybe resource constraints, maybe caution, maybe they're focused on other priorities. Or maybe, just maybe, there's something about having 2 bright comets simultaneously that feels off. That raises questions they're not ready to answer. That makes them uncomfortable promoting something they don't fully understand. Because here's the thing, if 2 comets arriving together is pure coincidence, if it's just randomness at work, then there's nothing to worry about. It's interesting, it's worth observing, but it's not alarming. But if there's a pattern, if this is the beginning of a trend, if cometary arrivals are increasing for reasons we don't yet grasp, then maybe silence is the safer option. Maybe waiting to see what happens next, waiting to gather more data, waiting to understand the bigger picture before making public statements. Maybe that's the prudent approach. I don't know. And 28 days after SWAN's discovery, with 11 days until its closest approach, with Lemon also approaching peak brightness, we're still left with coincidence as the official explanation. 2 comets, same month, pure chance. And maybe that's true. Maybe there's nothing more to it. But the silence from institutions that should be celebrating this rare alignment, that feels like something more than caution. That feels like uncertainty. And uncertainty, when it comes from organizations that are supposed to have answers, is unsettling. While NASA stays silent, while ESA releases 4-sentence updates, while professional observatories hold their spectroscopic data for peer review months from now, there's another story unfolding. A parallel narrative. A distributed observation campaign being conducted not by institutions with billion-dollar budgets, but by individuals with backyard telescopes, DSLR cameras, and an internet connection. The amateurs are watching, and what they're finding doesn't match the official predictions. Let's start with magnitude estimates, because this is where the discrepancy first became obvious. As of October 9th, 2025, the official brightness estimate for Comet SWAN, based on the most recent data available from professional sources, is magnitude 6.0 to 6.3. That puts it right at the threshold of naked eye visibility. Technically visible under perfect conditions, dark skies, no moon, adapted eyes, but realistically requiring binoculars for comfortable observation. But amateur observers are reporting something different. On October 7th, an observer in Australia posted a magnitude estimate of 5.8 based on visual comparison with nearby stars. On October 8th, an observer in South Africa reported magnitude 5.6. On October 9th, multiple observers across the Southern Hemisphere are converging on estimates between 5.5 and 5.9. That's 0.3 to 0.7 magnitudes brighter than the official estimate. And in astronomical terms, that's significant. Each 0.1 magnitude difference represents about a 10% change in brightness. So 0.5 magnitudes brighter means the comet is roughly 60% brighter than officially stated. 60%. Now, amateur magnitude estimates are less precise than professional photometry. Amateurs compare the comet's brightness to nearby stars, estimating by eye which star it matches. That method is subject to error. Atmospheric extinction, the dimming of light as it passes through Earth's atmosphere, affects comets and stars differently. The comet's diffuse coma makes it harder to judge brightness compared to point source stars. So some discrepancy is expected, but 0.5 magnitudes consistently across multiple independent observers in different locations with different equipment. That's not random error. That's systematic. That's a pattern. And it suggests the comet is brightening faster than models predict. Now let's talk about the tail, because this is where amateur observations become really interesting. As of October 3rd, observers reported the tail exceeding 5 degrees. By October 6th, some estimates pushed it to 5.5 degrees. By October 9th, the most recent report suggests 6 degrees, possibly more in long exposure photographs that bring out fainter extensions. 6 degrees. That's 12 full moon diameters. That's a tail stretching across a significant portion of the sky, visible even in moderately light-polluted areas if you know where to look. But it's not just the length that's interesting, it's the structure. Multiple observers, using different equipment, different processing techniques, different exposure times, are reporting faint helical or corkscrew patterns in the tail. Not obvious, not dramatic, but there. Subtle spirals, visible in stacked long exposure images after careful processing. Now, here's where we need to be careful. Because when you start stacking images, when you start applying contrast enhancement and noise reduction and all the digital processing tricks that astrophotographers use, you can create artifacts. You can see patterns that aren't really there, structure imposed by the processing algorithms rather than genuine features in the comet. So, is the helical structure real, or is it artifact? The answer is, we don't know. Because professional observatories haven't released high-resolution images showing the tail in detail. No Hubble images. No ground-based adaptive optics images. No professional confirmation or refutation. We have amateur images showing structure. And we have silence from professionals who have the equipment to definitively resolve the question. But here's why the amateur observations are worth taking seriously. Multiple independent observers are seeing the same thing. Different cameras, different telescopes, different locations, different processing workflows, and they're all reporting faint spiral structure. If it were pure artifact, if it were just noise being interpreted as signal, you'd expect the reports to be more random. Some observers seeing spirals, others seeing straight tails, others seeing no structure at all. Instead, there's consistency. The reports align, which suggests there might be something real there. And if the spiral structure is real, it tells us something important. It tells us the nucleus is rotating, releasing jets of gas and dust from localized active regions. As the nucleus spins, those jets trace out a corkscrew pattern in the tail. The rotation period, based on the observed spiral pitch, would be on the order of hours to a few days. That's consistent with typical cometary rotation, and it suggests the nucleus isn't a uniform, spherical object, but something irregular, with preferential outgassing from specific locations. But again, we don't know for certain because the professionals aren't publishing. Now let's talk about color, because this is another area where amateur observations are raising questions. Comets typically have a greenish tint. That color comes from diatomic carbon, C2, and cyanogen, CN, molecules that emit light at specific wavelengths in the green part of the spectrum when excited by solar ultraviolet radiation. SWAN is green. That's been reported by multiple observers. Green coma, visible even in binoculars under dark skies. But some observers are claiming the green is unusually intense, more vivid than typical comets, more saturated. Is that real? Or is it subjective? Are observers seeing what they expect to see? A comet with a green coma, and interpreting normal green as unusually intense because they're primed to see something unusual? Hard to say without spectroscopy. Without measuring the exact emission lines, quantifying the C2 and CN abundances, comparing them to other comets. And that spectroscopic data exists somewhere. Professional observatories have spectrographs. They've almost certainly observed SWAN, but they haven't released the data, so we're left with amateur descriptions. The green looks really intense, more green than I've seen in other comets. Subjective, unquantified, but consistent across multiple reports, which raises the question: if the green is unusually intense, what does that mean? High C2 and CN abundance suggests high carbon content, which is consistent with a carbon-rich comet, possibly dominated by CO and CO2 rather than water ice. And carbon-rich comets tend to be more active, outgassing more vigorously, brightening faster than water-dominated comets, which would explain the magnitude discrepancy, which would explain the rapid tail growth, which would tie everything together into a coherent picture. But without spectroscopy, it's speculation. Now let's talk about the coordination happening in amateur communities, because this is where things get really interesting. On Reddit, in the R Comet subreddit and R Astronomy, there are threads dedicated to SWAN observations, hundreds of comments, daily updates from observers around the world, magnitude estimates compared and cross-checked, tail length measurements averaged across multiple reports, photographs shared and analyzed. On cloudy nights, one of the largest online astronomy forums, there's a 30-page thread on SWAN. Observers posting their images, their observations, their questions, discussions about processing techniques, about whether the spiral structure is real, about why the comet seems brighter than predictions. On Discord servers dedicated to amateur astronomy, there are channels specifically for SWAN, real-time coordination. I'm observing now, magnitude looks like 5.7 to me. I'm in South Africa, I agree, definitely brighter than 6.0. Just took a photo, tail is at least 6 degrees, maybe 6.5. This isn't casual observation, this is systematic data collection, distributed across time zones, across continents, creating a global observation network that rivals professional capabilities. And what that network is finding is that SWAN is consistently brighter, consistently more active, consistently more interesting than the official numbers suggest. But here's where it gets frustrating. When amateur observers point this out, when they post on forums saying, the official estimate is magnitude 6.3, but I'm seeing 5.7, the response from professional astronomers, on the rare occasions they engage, is dismissive. Amateur visual estimates are imprecise. True. But when dozens of amateurs in different locations with different equipment all report the same discrepancy, it's worth taking seriously. You're probably overestimating the brightness because the comet's diffuse appearance makes it look brighter than it is. Possible, but experienced amateur observers know how to account for that. The official estimates are based on professional photometry, which is more accurate, maybe. But if that professional photometry isn't publicly available, if we can't see the data and verify the methods, how do we know? And that's the core of the frustration. Amateurs are observing, measuring, sharing data openly. Professionals are presumably doing the same, but holding the results for later publication. And in the gap between those two approaches, trust erodes. Now let's talk about censorship, because this is where amateur observations intersect with institutional control in ways that are concerning. On October 5th, a Reddit user posted a detailed analysis of SWAN's brightness trend. He compiled magnitude estimates from multiple sources, fitted a brightening curve, extrapolated to October 20th, and concluded that the comet might reach magnitude 3.5, significantly brighter than the official prediction of magnitude 4 to 4.5. The post gained traction, hundreds of upvotes, dozens of comments discussing the analysis, debating the methods, sharing additional observations. And then, 12 hours later, the post was removed. Not by the user, by moderators. The stated reason? Unverified claims that may mislead readers. The user reposted, asking why compiling publicly available magnitude estimates and fitting a trend line constitutes unverified claims. The repost was also removed, this time with no explanation. The user is now shadow banned from the subreddit. His comments don't appear. His posts aren't visible. He effectively doesn't exist in that community anymore. What did he do wrong? He analyzed data. He showed his work. He arrived at a conclusion that differed from the official prediction. And for that, he was silenced. Now, to be fair, Reddit moderation is often heavy-handed. Moderators have broad discretion. They remove posts for all kinds of reasons, justified or not. This might be nothing more than overzealous moderation, an attempt to prevent misinformation by removing any analysis that contradicts official sources. But it creates a chilling effect. Other amateur researchers see what happened. They think twice before posting their own analysis. They self-censor, deciding it's safer to stay quiet than risk being banned. And that's a problem, because amateur analysis, even when wrong, even when flawed, contributes to the conversation. It challenges assumptions. It forces re-examination of data. That's how science progresses. Silencing amateur voices doesn't protect against misinformation. It just concentrates authority in institutions that are already staying quiet. Similar patterns are emerging on other platforms. YouTube videos analyzing SWAN's brightness discrepancies have been demonetized, not removed, but flagged as not suitable for all advertisers. Creators report significant drops in viewership, suggesting algorithmic suppression. Twitter posts, or X posts, linking to amateur brightness analyses sometimes disappear from search results. Not deleted, but de-indexed, made effectively invisible unless you have the direct link. Again, this might be coincidental. Algorithm changes, automated content moderation catching false positives, nothing coordinated. But the pattern is there. Amateur observations that contradict official predictions are being marginalized, deplatformed, made harder to find. And that raises a question. Why? If the amateur observations are wrong, if they're based on flawed methodology or misinterpreted data, why not engage with them? Why not explain the errors, provide better data, demonstrate why the official predictions are correct? Instead, silence from professionals, removal from platforms, a sense that asking questions, sharing observations, analyzing data, all of it is somehow unwelcome. And that's how trust dies. That's how institutional authority erodes. Because when people feel like they're being silenced, they assume it's because they're onto something. They assume the censorship validates their conclusions. Whether that's true or not almost doesn't matter. The perception is enough. So here's where we stand. 28 days after discovery, 11 days until closest approach. Amateur observers around the world tracking SWAN, measuring its brightness, photographing its tail, sharing data in real time, and finding that the comet is brighter, more active, more dynamic than official sources acknowledge. Whether that discrepancy is real or artifact, whether the amateurs are right or the professionals are right, we won't know until October 20th. Until the comet reaches closest approach and we can compare predictions to reality. But the silence from institutions, the suppression of amateur analysis, the gap between what observers are seeing and what authorities are saying, all of it creates a vacuum. And in that vacuum, questions multiply, trust erodes, and the sense that something is being hidden, whether justified or not, becomes impossible to shake. 11 days. That's all that remains between now, October 9th, 2025, and the moment Comet C 2025 R2 SWAN will make its closest approach to Earth. 11 days until October 20th. 11 days until we find out if this comet meets expectations, exceeds them, or surprises us in ways nobody has predicted. And here's what NASA has told you to expect. Magnitude 4 to 6. Visible with binoculars under dark skies. Possibly visible to the naked eye if you're in the southern hemisphere with perfect conditions. A nice opportunity for amateur astronomers. A pleasant celestial event. That's the official line. But let's talk about what they're not saying. What they're not preparing you for. What might happen on October 20th if the amateur observations are correct and the professional estimates are wrong? Let's start with the brightness predictions, because this is where the discrepancy is most glaring. Official estimate as of October 9th, magnitude 6.0 to 6.3. That's based on professional photometry, orbital calculations, standard cometary brightening models. Amateur consensus as of October 9th, magnitude 5.5 to 5.9. That's based on visual estimates from multiple independent observers across the southern hemisphere, cross-checked against star charts, averaged to reduce individual error. Half a magnitude difference, maybe more. Now, if the comet is already 0.5 magnitudes brighter than official estimates suggest, and if that trend continues, what does that mean for October 20th? The official prediction for October 20th is magnitude 4, maybe magnitude 3.5 if things go well. But if the current brightening rate holds, if the amateur observations are accurate, we're looking at magnitude 3, maybe magnitude 2.5. And magnitude 2.5 is not nice celestial event territory. Magnitude 2.5 is bright, unmistakable, visible from suburban areas, visible even with moderate light pollution. That's a comet that casual observers will notice. That's a comet that will generate headlines. But here's where it gets really interesting. Because magnitude predictions assume linear or near-linear brightening as the comet approaches Earth. They assume the outgassing rate stays relatively constant, that the nucleus doesn't fragment, that nothing unexpected happens. But what if something unexpected does happen? Scenario 1. Outburst. Comets can experience sudden, dramatic increases in brightness caused by outbursts. An outburst occurs when a pocket of volatile gas trapped beneath the nucleus surface suddenly vents into space, or when solar heating cracks the nucleus crust, exposing fresh ice, or when the nucleus rotation brings a particularly active region into direct sunlight. Outbursts can increase a comet's brightness by a factor of 10 or more in a matter of hours. Magnitude 4 becomes magnitude 1. Magnitude 3.5 becomes magnitude 0.5. Suddenly, you're looking at a comet rivaling the brightest stars in the sky. Has SWAN shown signs of outburst activity? Maybe. The rapid brightening between September 16th and September 22nd, when predictions were revised upward by a full magnitude, could have been an outburst. Or it could have been normal brightening that we simply didn't observe accurately because of the solar glare. But if it was an outburst, that means the nucleus is unstable. That means it's releasing gas in unpredictable surges. And that means another outburst could happen between now and October 20th, or on October 20th itself. What would that look like? Imagine checking the comet on October 19th. Magnitude 4, as predicted. Nice, but not spectacular. Then you check again on October 20th. Magnitude 1. Suddenly one of the brightest objects in the night sky. A tail stretching 10, 15, 20 degrees. Visible from anywhere with a clear view of the horizon. That's what an outburst can do. And comets, approaching the sun, heated by intense radiation, under thermal stress, are prime candidates for outburst events. Is NASA prepared for that possibility? Have they mentioned it in any public statements? No. Radio silence. Scenario 2. Fragmentation. Cometary nuclei are loosely bound collections of ice and rock. They're not solid bodies. They're what planetary scientists call rubble piles, held together by weak gravity and structural cohesion. And when a comet gets too close to the sun, when thermal stress builds up, when tidal forces from solar gravity or rotation-induced centrifugal forces exceed the cohesive strength of the nucleus, it can break apart. Fragmentation is not rare. It happened to Comet 73P Schwarzmann-Bachmann 3 in 2006. The nucleus split into dozens of fragments, each releasing its own cloud of gas and dust. The result was a dramatic brightening, followed by a gradual fade as the fragments dispersed. It happened to Comet Linear in 2000. The nucleus disintegrated entirely, creating a cloud of debris visible in telescopes, but quickly fading as the fragments spread out. It happened to Comet Ison in 2013. As Ison passed within 1.2 million kilometers of the Sun, it broke apart, disappointing millions who had been promised the comet of the century. Could it happen to SWAN? Absolutely. SWAN passed perihelion on September 12th. That was the moment of maximum solar heating, maximum thermal stress. If the nucleus was going to fragment due to solar proximity, that's when it would have happened. But SWAN survived perihelion intact, or at least it appeared to. No reports of multiple condensations in the coma, no obvious signs of breakup. But fragmentation doesn't always happen instantly. Sometimes it's delayed. The nucleus cracks at perihelion, but doesn't fully separate until days or weeks later, when rotation or outgassing finally pulls the pieces apart. So fragmentation could still happen between now and October 20th. Or after. What would that look like? Depends on how the nucleus breaks. If it splits into 2 or 3 large pieces, each piece would develop its own coma and tail, creating a spectacular multi-tailed comet visible for weeks. Brightness would surge as fresh ice is exposed. If it shatters into dozens of smaller pieces, brightness would initially spike, then fade rapidly as the fragments disperse and lose mass to outgassing. If it disintegrates completely, the comet disappears. A cloud of debris replaces the bright nucleus, fading within days. And here's the thing. We have no way to predict which scenario would occur because we don't know the nucleus size, structure, or internal cohesion. We don't have high-resolution imaging. We don't have spectroscopy showing compositional heterogeneity that might indicate weak zones prone to fracture. We're flying blind. And on October 20th, we'll find out if the nucleus holds together or comes apart. Scenario 3. The amateur observers are right. This is the simplest scenario. No outbursts, no fragmentation, just a comet behaving exactly as the current observations suggest, brightening at the rate amateur estimates indicate, reaching magnitude 3 or 2.5 on October 20th. If that happens, it means the professional estimates were wrong. Not catastrophically wrong, but measurably wrong. Half a magnitude or more off the mark. And that raises questions. Why were the professional estimates conservative? Was it caution? An attempt to avoid overhyping a comet that might disappoint? Was it poor data? Reliance on outdated models that don't account for SWAN's unusual composition or activity level? Or was it something else? Because if the amateurs, with their backyard telescopes and visual estimates, are getting more accurate brightness measurements than professionals with million-dollar photometric equipment, that's embarrassing. That's a failure of institutional capability. That's a sign that something is broken in the data pipeline between observation and public communication. And if SWAN does reach magnitude 2.5 or brighter, if it becomes one of the most visible comets in years, visible even from cities, capturing public attention in a way that few astronomical events do, NASA will have to explain why they didn't prepare people for it, why they didn't issue observation guides, press releases, social media campaigns, why they stayed silent while an historic event approached. Now let's talk about the tail, because brightness is just one metric. The tail is another. As of October 9th, amateur observers report the tail at 6 degrees, possibly more in long exposure photographs. That's already spectacular. That's a tail stretching across a significant portion of the sky, visible to anyone who takes the time to look. But tails grow. As comets approach Earth, as they continue outgassing, as solar radiation pressure pushes dust and ions away from the nucleus, tails extend. They can grow by degrees per day in the final approach. By October 20th, SWAN's tail could be 8 degrees, 10 degrees, maybe more. For reference, 10 degrees is 20 full moon diameters. That's a tail stretching from horizon to nearly halfway up the sky in some orientations. That's a tail visible to anyone, anywhere, who looks up. And if the tail develops structure, if the helical patterns that amateur observers are reporting become more pronounced, if disconnection events occur where sections of the tail break off and drift away, creating multiple streamers, the visual spectacle will be even more dramatic. Comet Hale-Bopp in 1997 had a tail that reached 30 degrees at peak. It dominated the evening sky for weeks. Millions of people saw it, photographed it, remembered it. SWAN won't match Hale-Bopp, but it could come close. And if it does, the silence from NASA and ESA will look even more conspicuous. Now, practical information. Because whether SWAN reaches magnitude 4 or magnitude 2, whether the tail is 6 degrees or 12 degrees, the question remains, how do you see it? Where to look? Eastern sky before dawn. The comet is currently in Libra, moving north. By October 20th, it will be approaching Serpens. For Northern Hemisphere observers, It will be low on the eastern horizon in the hour before sunrise. For southern hemisphere observers, it will be higher, more favorably positioned. What equipment? If the comet reaches magnitude 4, as officially predicted, binoculars are necessary. 7x50 or 10x50 binoculars will show the coma clearly and reveal the tail. If it reaches magnitude 3 or brighter, naked eye visibility becomes possible under dark skies. If it exceeds magnitude 3, you might see it from suburban areas. When to observe? The best viewing window is October 18th through October 22nd. The comet will be at or near peak brightness. The moon will be waning, reducing light pollution. Morning twilight begins later in October than in September, giving a darker observing window. Photography. A DSLR or mirrorless camera with a telephoto lens, 50mm to 200mm focal length, mounted on a tripod. Exposures of 10 to 30 seconds at ISO 1600 or higher. Take multiple shots, stack them to reduce noise, and you'll capture the tail in detail. But here's what nobody is officially telling you. If the amateur observations are correct, if SWAN is already brighter than predicted, then by October 20th, you might not need dark skies. You might not need to travel to remote locations. You might be able to step into your backyard, look east before dawn, and see it. A comet. Bright. Clear. Undeniable. And if that happens, the question everyone will be asking is, why didn't NASA tell us this was coming? Beyond October 20th, what happens next? The comet will begin to recede. It will fade, gradually at first, then more quickly as it climbs away from Earth and the Sun. By early November, it will drop below magnitude 6. By December, below magnitude 8. By early 2026, it will be too faint for amateur observation. But the data collected on October 20th will persist. Images, magnitude measurements, spectroscopy, if any professional observatory finally releases it. That data will either confirm the predictions or refute them. And if it refutes them, if SWAN proves to be brighter, more active, more spectacular than NASA and ESA said it would be, the silence leading up to October 20th will be remembered. Because that silence won't just be bureaucratic caution, it will be a failure. A failure to communicate, a failure to prepare, a failure to engage the public with an event that happens once in a human lifetime. 11 days. That's all we have left to wait. 11 days until we find out if the institutions we trust to tell us about the cosmos earned that trust or squandered it. The comet is coming. It doesn't care what NASA predicts. It doesn't care about peer review or publication schedules or institutional caution. It's coming. And on October 20th, we'll all see what it really is. This chapter was added after the original recording was completed. 48 hours ago, on October 7th, 2025, I finished writing chapters 1 through 8. I laid out the timeline. I documented the silence from NASA and ESA. I detailed the discrepancies between amateur observations and professional predictions. And I concluded with a simple statement. October 20th will be the moment of truth. But something happened in those 48 hours. Something that changes the narrative. Not dramatically, not in a way that resolves all the questions, but enough that this bonus chapter became necessary. Because the silence broke. On October 8th, 2025, multiple sources published updated information about Comet SWAN. USA Today ran a feature on the twin comets visible in October. Forbes posted an article titled, "Comet Tracker for Thursday. It's finally time to see rare twin comets." Starwalk Space updated their comet visibility guide with new brightness estimates. And most significantly, the SkyLive.com, which aggregates data from JPL's small body database, published updated orbital elements and magnitude predictions for SWAN. And those predictions are bizarre. According to the SkyLive's data, sourced from JPL, as of October 8th, Comet SWAN's predicted magnitude is 9.10, not magnitude 6, not magnitude 5.8, as amateurs are reporting. Magnitude 9.10, 9.1. That's invisible to binoculars. That's barely visible in small telescopes. That's 3 full magnitudes dimmer than what amateur observers around the world are actually seeing when they point their equipment at the comet right now. So what's going on? One possibility: JPL's database hasn't been updated. The magnitude 9.10 prediction is based on older orbital elements, older brightness models, and doesn't reflect the comet's current activity. That happens sometimes. Databases lag. Updates take time. The official numbers don't always keep pace with reality. But here's the problem. JPL's small body database is automated. It updates regularly as new observations come in. If observers are submitting brightness measurements to the Minor Planet Center, and those measurements are being processed, JPL's database should reflect them within days. So why the 3 magnitude discrepancy? Another possibility: the magnitude 9.10 value is a calculated prediction based on the comet's heliocentric distance and a standard brightness model, not an observed value. And that model is wrong because SWAN isn't behaving like a standard comet. Most comets brighten according to a formula that relates brightness to distance from the sun. As they get closer, they get brighter, following a predictable curve. But that curve assumes standard composition, standard outgassing rates, standard nucleus size. If SWAN is unusually active, if it's carbon-rich and outgassing vigorously, if its nucleus is larger than assumed, the standard formula fails. The calculated brightness diverges from reality. And if JPL's database is showing calculated values rather than observed values, that would explain the discrepancy. But it raises a question. If the calculated values are so far off, why hasn't JPL updated their model? Why are they still publishing magnitude 910 when anyone with binoculars can see that's wrong? Now let's talk about the other sources that published updates on October 8th, because their numbers are different. USA Today, citing expert sources, states that SWAN has an estimated brightness of magnitude plus 6.1. That's much closer to what amateurs are reporting. That's in the ballpark. Star Walk Space says magnitude 6, making it observable through binoculars and small telescopes. Again, consistent with amateur reports. Space.com, in an article from September 22nd that's been updated as recently as October 8th, cites predictions from comet experts Seiichi Yoshida and Gideon Van Buitenen suggesting the comet will peak somewhere between magnitude plus 6 and plus 7 around October 20th. And Daniel W.E. Green from the Central Bureau for Astronomical Telegrams suggests magnitude of plus 6 from Oct 2 to 20, perhaps becoming a few tenths brighter around Oct 12. So we have a consensus forming. Magnitude 6, give or take a few tenths, from early October through October 20th. Except, that contradicts what amateurs are seeing, because amateurs are reporting magnitude 5.5 to 5.9 as of October 9th, half a magnitude brighter than the expert consensus. And it contradicts what JPL's database is showing, which is magnitude 9.10, 3 magnitudes dimmer than the expert consensus. So we have 3 different narratives. 1. JPL database, magnitude 9.10, invisible in binoculars. 2. Expert consensus, magnitude 6.0 to 6.5, visible in binoculars. 3. Amateur observations, magnitude 5.5 to 5.9, easily visible in binoculars, approaching naked eye. One of these is wrong. Probably JPL's database, since it's the outlier. But the discrepancy between expert consensus and amateur observations remains unresolved. Now here's what makes the October 8th updates interesting. They represent the first coordinated public communication about SWAN in nearly 2 weeks. Since the 4-sentence ESA update on October 7th, there's been almost no institutional engagement. But on October 8th, multiple mainstream outlets published features. USA Today, Forbes, Space.com. Why October 8th? What triggered this sudden wave of coverage? One possibility: October 20th is 12 days away. That's close enough that procrastination is no longer an option. If these outlets are going to cover the twin comet event, they need to publish now, while there's still time for readers to prepare and observe. Another possibility: something changed. Some new observation, some data point, some development prompted coordination among science journalists and experts to push this story into public awareness. But if something changed, what was it? On October 7th and 8th, amateur observers reported another uptick in brightness. Estimates from October 6th had clustered around magnitude 6.0 to 6.2. By October 8th, those estimates had shifted to 5.7 to 5.9. That's 0.3 magnitudes brighter in 2 days. 0.3 magnitudes in 2 days is rapid, not unprecedented. Comets can brighten that fast during active outgassing or as Earth's viewing geometry improves. But it's notable. It's the kind of change that, if confirmed by multiple independent observers, would warrant attention. Did that brightness surge prompt the October 8th media coverage? Did science journalists, monitoring amateur reports, realize the comet was exceeding predictions and decide to publish? Maybe. Or maybe it's coincidence. Maybe October 8th was just when the articles were scheduled to run, based on editorial calendars planned weeks in advance. But the timing feels significant. Now let's talk about what didn't happen in the last 48 hours. What's still missing? NASA has not issued a press release specifically about SWAN. The Near-Earth Object Program website still has no dedicated content, no observation guides, no technical briefings. The only NASA mention remains the 2 Astronomy Picture of the Day features from September 16th and 18th. ESA has not expanded beyond their October 7th 4-sentence update. No additional technical details. No brightness forecasts. No engagement beyond minimal acknowledgement. Hubble has not released images. JWST has not released spectra. No professional observatory has published high-resolution data showing the nucleus, the tail structure, the compositional analysis that would settle the questions about what SWAN is and why it's behaving this way. The silence from institutions hasn't broken. It's just been bypassed. Mainstream media went ahead and covered the story without waiting for NASA or ESA to provide official briefings. And that's unusual. Science journalists typically rely on institutional sources. They interview NASA scientists. They cite ESA press releases. They wait for official data before publishing. Going ahead with coverage based primarily on amateur observations and independent expert opinions, without institutional backing, is a departure from normal practice. It suggests either frustration with institutional silence or confidence that the amateur observations are reliable enough to warrant coverage regardless of what NASA says or doesn't say. Now, what does this mean for October 20th? If the expert consensus is correct, if SWAN plateaus at magnitude 6 and holds there through October 20th, then it will be a nice binocular object. Visible, interesting, worth observing, but not spectacular, not headline-making. If the amateur observations are correct, if SWAN is already magnitude 5.8 and continues brightening at the current rate, then by October 20th, we're looking at magnitude 5.0, possibly magnitude 4.5. That's approaching naked eye territory. That's a comet that will generate public excitement. That's an event. And if JPL's magnitude 9.10 prediction is somehow correct, if the comet is about to fade dramatically, and all the current observations are misinterpreting outburst activity that's already subsiding, then October 20th will be a disappointment, a fizzle, a repeat of ISON. 10 days from now, we'll know which scenario played out. But here's what the last 48 hours revealed. The institutions aren't leading this story. The media is covering it independently. The amateur community is providing the real-time data. And the discrepancies between what different sources are saying, JPL versus experts versus amateurs, remain unresolved. That's not how it's supposed to work. NASA is supposed to be the authoritative source. ESA is supposed to provide coordinated updates. The data pipeline from observation to publication to public communication is supposed to flow smoothly, with institutions guiding the narrative. Instead, we have fragmentation. We have competing predictions. We have amateur observers reporting one thing, experts predicting another, and NASA saying almost nothing. And in 10 days, on October 20th, reality will arbitrate. The comet will either meet expectations, exceed them, or fall short. And whichever outcome occurs, the silence from NASA and ESA in the days leading up to it will be part of the story. Because this isn't just about a comet anymore. It's about trust. It's about whether the institutions we fund to monitor the skies, to characterize near-Earth objects, to engage the public with astronomical events, are fulfilling that mandate. And based on the last 48 hours, based on the fact that mainstream media is covering this story without NASA's involvement, based on the fact that amateur observers are driving the narrative while professionals stay quiet, the answer is increasingly clear. They're not. The comet is coming. October 20th is 10 days away. And whether NASA is ready or not, whether ESA has anything to say or not, whether the institutions acknowledge it or not, the global community of observers will be watching. And we'll find out if the silence was caution or if it was something else. Stay subscribed. Because in 10 days, this story reaches its conclusion. And whatever happens on October 20th, you'll want to be part of it. The silence is breaking, but the answers are still 10 days away. 10 days. That's all that remains. October 9th, 2025. 10 days until October 20th. 10 days until Comet C 2025 R2 SWAN makes its closest approach to Earth at a distance of 0.26 astronomical units, 39 million kilometers, 24 million miles. And after everything, after 28 days of watching, after documenting the amateur observations, after tracking the institutional silence, after analyzing the discrepancies, the questions, the patterns that don't quite add up, here's where we stand. The comet is magnitude 6.1, according to Wikipedia, as of October 8th. Magnitude 6.6, according to the SkyLive, citing COBS, the Comet Observation Database. Magnitude 6.2, according to amateur visual observer Marco Goyato on September 26th. Magnitude 5.9, according to reports from Southern Hemisphere observers in early October. Take your pick, because even now, 10 days from closest approach, we don't have consensus on the basic question of how bright this comet actually is. And NASA? Still silent. No press release. No dedicated observation guide. No technical briefing explaining the brightness variations, the tail structure, the compositional analysis. ESA? Still minimal. That 4-sentence October 7th update remains the extent of their public communication beyond standard APOD features. The professionals? Still holding their data. Spectroscopy, high-resolution imaging, photometric light curves, all of it presumably exists, collected by observatories around the world, but none of it publicly released. So here we are, 10 days out, and the story is still being told, not by institutions, but by individuals, by amateur observers posting magnitude estimates on forums, by science journalists piecing together articles from independent expert opinions, by YouTube creators like me trying to make sense of incomplete information and institutional silence. This isn't how it's supposed to work. This isn't how major astronomical events are supposed to unfold. There should be coordination. There should be clear communication. There should be authoritative guidance from the organizations we fund specifically for this purpose. Instead, we have fragmentation. Multiple contradictory predictions. Amateurs filling the void left by professional silence. And a growing sense that something about this comet, or about the response to it, is deeply, fundamentally off. But let's step back. Let's assess what we actually know, as opposed to what we suspect, or question, or wonder about. We know C 2025 R2 SWAN exists. It was discovered September 11th, 2025, by Vladimir Bezugliy using SOHO imagery. That's confirmed. That's undisputed. We know it passed perihelion on September 12th at 0.5 AU from the Sun. That's orbital mechanics. That's verified. We know it will make closest approach to Earth on October 20th at 0.26 AU. That's not in question. The geometry is straightforward. The date is certain. We know it's currently visible in binoculars. Multiple observers, different locations, different equipment, all confirm this. Whether it's magnitude 6.6 or 6.1 or 5.9, it's visible. That's real. We know it has a tail. Observers report 5 to 6 degrees, possibly more. Photographs show clear tail structure. That's documented. So the comet is real. It's approaching. It's visible. All of that is fact. What we don't know, what remains uncertain, is why the professional community has been so quiet. Why the brightness estimates vary so widely. Why spectroscopic data hasn't been released. Why there's been minimal institutional engagement with an event that by all accounts is worth engaging with. And that uncertainty, that gap between what should be happening and what is happening, has created space for all the questions this series has explored. The timeline gaps, the amateur versus professional discrepancies, the sense that something isn't being said. But here's the thing. Maybe the simplest explanation is the correct one. Maybe there's no conspiracy. Maybe there's no hidden data. Maybe institutions are just slow, cautious, under-resourced, focused on other priorities, and unwilling to hype a comet that might not meet expectations. Maybe SWAN is just a comet, brightening as it approaches Earth, outgassing as solar radiation heats its nucleus, following the same physical processes every comet follows, and all the anomalies, all the questions, all the discrepancies are just normal variability, normal uncertainty, normal messiness that happens when you're trying to characterize a new object with limited data. Maybe. Or maybe there's something more. Something about SWAN's composition, or its behavior, or the observations being collected that doesn't fit standard models. Something that professionals are still trying to understand before making public statements. Something that explains the caution, the delayed communication, the silence that feels, from the outside, like evasion. We won't know until October 20th. until the comet reaches closest approach and we can compare predictions to reality. Until we see whether it reaches magnitude 4, like the conservative estimates suggest, or magnitude 3, like the optimistic predictions indicate, or something else entirely. And here's what will happen on October 20th. Regardless of brightness, regardless of tail structure, regardless of everything we've discussed over these 10 chapters, observers around the world will point their equipment at the eastern sky before dawn. They'll locate SWAN in Serpens or Aquila, depending on their latitude and exact timing. They'll capture images, they'll estimate magnitudes, they'll measure tail lengths, and they'll share that data. Within hours, we'll know. The global amateur network, coordinating through forums and Discord servers and social media, will generate real-time observational data that settles the questions. Is it magnitude 4? Magnitude 3? Brighter? Fainter? And within days, that data will be compiled, analyzed, compared to predictions. The discrepancies will be quantified, the models will be tested, and we'll know whether the professional estimates were accurate or whether the amateurs were right all along. But here's what won't happen. We won't get immediate clarity from NASA or ESA. We won't get press conferences explaining why the predictions were off if they turn out to be off. We won't get transparency about what data was collected, when it was collected, and why it wasn't shared earlier. Because institutions move slowly. Publications take months. Peer review takes time. And by the time professional papers are published analyzing SWAN's October 20th behavior, the comet will be fading, receding, becoming a memory rather than an active event. The story will be over. And the questions about why it unfolded the way it did, why there was so much silence, why amateur observers seemed to be ahead of professionals, those questions will remain unanswered. Or answered only in passing, in footnotes, in acknowledgement sections of papers published months later. So what's the point of all this? What's the point of 10 chapters documenting silence, tracking discrepancies, raising questions that might not have answers? The point is this: astronomy is changing. The relationship between professionals and amateurs, between institutions and individuals, between authority and distributed observation networks, all of it is in flux. Amateurs discovered SWAN. Amateurs provided the real-time brightness estimates. Amateurs documented the tail structure. Amateurs drove the narrative while professionals stayed quiet. And whether that's a failure of institutions or an evolution of the field, whether it's something to criticize or something to celebrate, it's happening. The democratization of astronomy, the rise of citizen science, the shift from centralized authority to distributed collaboration. SWAN is just one example, but it's a clear one, a bright one, an object that should have been institutional property, announced and studied and communicated through official channels, but instead became a community project, tracked and analyzed and shared through networks of individuals who don't need permission or funding to participate. Maybe that's the real story here. Not the comet itself, not the brightness discrepancies, or the tail structure, or the orbital uncertainties, but the way the story was told. By whom? Through what channels? With what gaps between institutional knowledge and public awareness? 10 days from now, on October 20th, we'll find out if SWAN lives up to expectations. We'll see the images. We'll read the magnitude reports. We'll know whether this was a spectacular comet or a modest one, whether the predictions were accurate or flawed. But we already know the institutional response was inadequate. 28 days of minimal communication. No coordinated observation campaigns. No public engagement matching the event's potential significance. That's not speculation. That's fact. Documented across 10 chapters, backed by the absence of press releases, the paucity of official updates, the silence where there should have been guidance. And that silence tells a story about priorities, about caution, about institutional reluctance to engage unless certainty is absolute. A story about the gap between what the public wants, real-time information and participatory excitement, and what institutions provide, delayed publications and carefully hedged statements. SWAN will fade. By November, it'll be magnitude 8. By December, magnitude 10. Invisible to all but the most dedicated amateur observers with powerful telescopes. By early 2026, it'll be gone, climbing back out toward the Oort cloud on its centuries-long orbit. But the questions raised by how this event was handled, or not handled, those will persist. Those will shape how future comets are communicated. Those will influence whether institutions adapt to the new reality of distributed observation and real-time sharing, or whether they continue operating on timescales and communication strategies designed for a pre-internet era. 10 days remain. The comet is coming. And whether NASA is ready, whether ESA has anything to say, whether the institutions acknowledge it or not, the global community of observers will be watching, recording, sharing. Because the sky doesn't belong to institutions. It belongs to anyone who looks up. And the tools to observe it, to measure it, to understand it, are no longer exclusive to professionals with advanced degrees and institutional funding. They're in the hands of individuals, distributed across continents, coordinating through networks that operate faster than peer review, faster than official channels, faster than institutional caution. Vladimir Bezugliy found a comet. Amateurs tracked it. The community documented it. And in 10 days, on October 20th, that community will observe its closest approach and determine whether the predictions were right. The institutions can publish their papers later, months from now, behind paywalls, in journals most people will never read. But the story is being written now, by observers, by individuals, by the global network of people who didn't wait for permission to watch the sky. The silence continues, but the comet doesn't care. It's coming, and we'll all see what it is. 10 days.